In this video, we are going to learn what is the shape of the universe actually. Does the universe even have a shape, or it is just the random expansion in all directions? Are there any crazy theories that try to explain about the actual shape of the universe? This video is going to be very cool to learn if you are space enthusiasts like me. Let me know before the start of this video. What do you think the shape of the universe is? So, let's get started. Chapter 1. Picture yourself standing in an open field on a clear night. The grass beneath your feet stretches out in every direction until it meets the horizon. Above you, thousands of stars pierce through the darkness like tiny holes in a cosmic curtain. And then, suddenly a question bubbles up from somewhere deep in your mind. A question so simple that a child might ask it, yet so profound that the greatest minds in history have wrestled with it. Where does all of this end? Does the universe just keep going forever and ever? Or does it eventually stop somewhere? And if it stops, what's on the other side of that stopping point? Maybe there is no end and no edge. Maybe trying to find the edge of the universe is like trying to find the edge of the surface of a ball. You can walk around a ball forever and never fall off, never reach a boundary, even though the ball itself is finite. For most of human history, this question lived purely in the realm of imagination and philosophy. Ancient priests and poets wondered about it. They told stories about it, but they had no real way to answer it. They could only guess, only dream, only create elaborate myths that felt true, even if they had no evidence. But something remarkable happened in the last 100 years or so. For the first time in all of human existence, we actually developed the tools to investigate this question scientifically. We built telescopes that could see across billions of light years. We created mathematical frameworks that could describe the fabric of space itself. We launched satellites beyond our atmosphere to measure radiation that's been traveling through space since the universe was young. Now, here's why this question matters more than you might think at first. Understanding the shape of the universe isn't just some abstract puzzle that only concerns mathematicians and physicists locked away in their laboratories. The answer tells us something fundamental about our origins. It tells us where we came from. It reveals whether the universe will exist forever or whether everything that exists will eventually come to an end. It helps us understand whether we're living in a universe that will keep expanding infinitely, growing colder and emptier with each passing billion years, or whether gravity will eventually win and pull everything back together in a massive collapse. Think about that for a moment. The shape of the universe determines its ultimate fate. Just like knowing the shape of a ship helps you predict whether it will stay afloat or sink, knowing the shape of the cosmos helps us predict whether existence itself has a future or an expiration date. So we're going to take a journey together. We'll start in ancient Greece, where brilliant thinkers first began using logic and mathematics to understand the heavens. We'll travel through the Renaissance, when brave scientists challenged everything humanity thought it knew. We'll witness Einstein's revolutionary insight that space itself can bend and curve like a flexible fabric. We'll peer into the early moments of the Big Bang, when the entire universe was smaller than an atom, and we'll arrive at the cutting edge of modern cosmology, where satellites map the oldest light in the universe and powerful computers simulate cosmic evolution. Along the way, we'll meet the remarkable human beings who piece together this cosmic puzzle. People who dedicated their lives to answering this question. People who faced ridicule, who challenged authorities, who spent lonely nights at telescopes, who filled chalkboards with equations that changed how we see reality. Their story is our story, because every answer they found belongs to all of humanity. And here's what makes this question so utterly captivating. The answer turns out to be far stranger than anyone imagined. Stranger than the wildest science fiction. Stranger than the most elaborate myths. The universe we actually live in is more bizarre, more elegant, and more wonderful than even the most creative minds could have dreamed up just a few centuries ago. Chapter 2. How we think about shapes. Before we can possibly understand what shape the universe has, we need to take a step back and think carefully about what we even mean when we talk about shape. This might seem obvious at first. After all, you know what a ball looks like. You know what a box looks like. You understand that a piece of paper is flat and that an orange is round. These concepts feel so natural, so intuitive, that you probably don't give them much thought in daily life. But here's where things get interesting. The shapes you're familiar with exist in the three-dimensional space that you live in. You can walk forward and backward. That's one dimension. You can walk left and right. That's a second dimension. You can jump up or crouch down. That's a third dimension. Your brain is beautifully adapted to understand and navigate this three-dimensional world because your survival has depended on it for millions of years of evolution. Now, let me introduce you to dimensions in a way that might reshape how you think about space itself. Imagine a tiny ant living on a perfectly straight wire. That ant can only move in two directions along that wire. It can go forward or it can go backward. For that ant, the entire universe is one-dimensional. It has length, but no width and no height. The ant has no concept of left and right because left and right simply don't exist in its world. Now imagine that ant somehow gets transferred onto a huge piece of paper. Suddenly its world explodes with new possibilities. Now it can go forward and backward like before, but it can also go left and right. The ant is now living in a two-dimensional universe. It can explore area, not just length. But there's still no such thing as up and down in the ant's experience. If you placed your finger above the paper, the ant would have no way to detect it because the dimension of height doesn't exist in its flat world. We humans live in what we call a three-dimensional space. We can move forward, backward, left, right, and up, down. But here's the mind-bending question. What if there are additional dimensions that exist, but that we simply can't perceive? Just like the ant on the paper can't perceive the dimension of height, even though we can see it clearly, maybe there are dimensions of space that exist beyond the three we experience. Maybe the universe extends in directions that our brains literally cannot visualize or comprehend directly. This isn't just wild speculation. Many modern physics theories, particularly string theory, actually require the existence of additional spatial dimensions. These theories suggest that reality might have 10 or 11 total dimensions, but the extra dimensions beyond our familiar 3 are curled up so incredibly small that we can't detect them in everyday life. Now here's where our understanding of dimensions connects directly to the shape of the universe. When we ask what shape the universe has, we're really asking about the geometry of space itself. And geometry can work very differently depending on how many dimensions you're dealing with and how those dimensions are arranged. Let me give you an example that will help build your intuition. Take a flat piece of paper and draw a triangle on it. Now measure the 3 angles inside that triangle and add them up. If you measure carefully, you'll find they add up to exactly 180 degrees. This is something you probably learned in school. It seems like a fundamental truth about triangles. But now imagine drawing a triangle on the surface of a ball, like a globe. Start at the North Pole, draw a line down to the equator, draw another line along the equator for a while, then draw a third line back up to the North Pole. You've created a triangle, but here's the weird part. If you measure the angles of this triangle and add them up, you'll get more than 180 degrees. The bigger the triangle, the more the angles exceed 180 degrees. This happens because the surface of the ball is curved in a particular way. The geometry on a curved surface is fundamentally different from the geometry on a flat surface. And if the surface curved the opposite way, like a saddle shape, the angles of a triangle would add up to less than 180 degrees. This same principle applies to the universe itself, just in 3 dimensions rather than the 2 dimensions of a surface. The universe could be flat, like an infinite sheet of paper, where all the familiar rules of geometry apply. It could be positively curved, like the surface of an enormous sphere. Or it could be negatively curved, like an infinite saddle shape. Each possibility leads to a universe with fundamentally different properties and a fundamentally different ultimate fate. Here's the crucial insight that connects everything together. When we talk about the shape of the universe, we're not talking about a shape that you could view from the outside, like looking at a ball sitting on a table. We're talking about the intrinsic geometry of the space we live in. Just like the ant on the paper can determine whether its universe is flat or curved by doing geometry experiments without ever leaving the surface. We can determine whether our universe is flat or curved by making careful measurements of angles, distances, and how light travels through space. Understanding dimensions and geometry is the foundation we need to grasp what scientists mean when they talk about cosmic shape. With this foundation in place, we're ready to explore how humans first began contemplating these questions thousands of years ago. Chapter 3: The Ancient Dreamers. Long before telescopes, long before mathematics as we know it, long before the scientific method itself, humans looked up at the night sky and wondered. They wondered with the same intensity and curiosity that drives scientists today. These ancient observers didn't have our technology, but they had something equally valuable. They had eyes, they had minds, and they had the patience to watch the heavens night after night, year after year, generation after generation. The Babylonians, who lived in ancient Mesopotamia, between the Tigris and Euphrates rivers, were among the earliest careful sky watchers. They tracked the movements of the planets with remarkable precision. They noticed that 5 bright objects in the sky, what we now call Mercury, Venus, Mars, Jupiter and Saturn, moved against the background of fixed stars. They called these wanderers, which is what the word planet actually means. But when the Babylonians imagined the shape of the cosmos, they pictured something that made intuitive sense based on what they could see. The Earth was a flat disk floating on an infinite ocean of water. Above the disk was a solid dome, a great celestial bowl, and the stars were holes in that dome, allowing divine light to shine through from whatever lay beyond. The ancient Egyptians had a similar view, though their cosmology was more elaborate and tied intimately to their religious beliefs. They imagined the sky as a goddess named Nut, whose body arched over the earth. The sun god Ra travelled across her body during the day and through the underworld at night. These weren't just stories to the Egyptians. This was their understanding of reality. The shape of the universe was inseparable from their spiritual worldview. Then something remarkable happened in ancient Greece, beginning around 500 years before the Common Era. Greek philosophers started doing something revolutionary. They began using logic and mathematics to question everything, including the shape of the Earth and cosmos. They weren't satisfied with mythological explanations. They wanted to understand the universe through reason and evidence. A mathematician and philosopher named Pythagoras made a proposal that must have seemed absolutely insane to his contemporaries. He suggested that the Earth itself was a sphere, a ball floating in space. Think about how counterintuitive this idea was. When you look around, the Earth appears flat. If you pour water on the ground, it doesn't curve around a ball, it spreads out on a flat surface. If the Earth were a ball, wouldn't people on the bottom fall off? Wouldn't water drain away? The whole concept seemed to violate common sense. But Pythagoras and his followers weren't just making wild guesses. They had reasons for their belief. They noticed that the Earth cast a round shadow on the moon during lunar eclipses. If the Earth were a flat disk, the shadow would sometimes be elongated or oval, depending on the angle. But the shadow was always round, suggesting the Earth was spherical. They also developed mathematical and philosophical arguments. They believed that the sphere was the perfect shape, and therefore the cosmos and its parts should reflect this perfection. A few centuries later, a philosopher named Aristotle gathered even more evidence for a spherical Earth. He pointed out something that careful observers would have noticed. When you watch a ship sail away from shore, it doesn't just get smaller and smaller until it disappears. Instead, the ship appears to sink into the sea, with the hull disappearing first and the sails remaining visible longest. This is exactly what you'd expect if the surface of the ocean curves downward as you move away. On a flat Earth, you'd see the entire ship getting smaller uniformly until it vanished in the distance. Aristotle made another brilliant observation. Different stars are visible depending on how far north or south you travel. If you journey north, New stars appear near the northern horizon, while stars in the south dip below the southern horizon. This makes perfect sense if you're moving across the curved surface of a sphere, changing your viewing angle. But it makes no sense if the Earth is flat. On a flat Earth, the same stars should be visible everywhere, just at different angles. These Greek thinkers established something crucial for all of science that came after. They demonstrated that you could use careful observation combined with logical reasoning to understand the true structure of nature, even when that truth contradicted immediate appearances and common sense. But the Greeks didn't stop with just figuring out that Earth was a sphere. They also developed elaborate models for the entire cosmos. They imagined the universe as a series of nested transparent spheres, all centered on the Earth. The moon sat on the innermost sphere. Then came the spheres carrying the Sun, Mercury, Venus, Mars, Jupiter, and Saturn. Finally, the outermost sphere held all the fixed stars. Each sphere rotated at its own rate, which explained why different celestial objects moved at different speeds across the sky. Was this model correct? No, absolutely not. The Earth is not the center of the universe. There are no crystalline spheres carrying the planets around. But here's what matters. The Greeks established a method. They showed that humans could use observation, mathematics, and reason to understand cosmic structure. They proved that the universe operates according to principles that minds can comprehend. This intellectual foundation, this faith that the cosmos is understandable, became the bedrock of all science that followed. One Greek astronomer named Aristarchus even proposed something truly radical around 230 years before the Common Era. He suggested that maybe the Earth moved around the Sun, not the other way around. He was essentially correct nearly 1800 years before Copernicus would make the same argument. But Aristarchus's idea was rejected by most ancient thinkers. It seemed absurd. If the Earth were moving, wouldn't we feel it? Wouldn't everything not attached to the ground get left behind? These ancient dreamers, working with nothing but their eyes and their minds, took the first crucial steps toward understanding cosmic shape. They were wrong about many details, but they were right about something far more important. They were right that human beings could investigate these questions systematically. They were right that the universe follows discoverable patterns. They laid the groundwork for a revolution that would eventually overturn their own conclusions and reveal a cosmos far stranger and more magnificent than they ever imagined. Chapter 4. The revolution begins. For more than 1,000 years after the ancient Greeks, the prevailing view of the cosmos remained essentially unchanged. The Earth sat motionless at the center of creation. The sun, moon, planets and stars all revolved around us. This wasn't just a scientific theory, it was woven into philosophy, theology, and humanity's understanding of our place in the grand scheme of things. We were central. We were special. The entire cosmic machinery existed for our benefit. Then, in the year 1543, a Polish mathematician named Nicolaus Copernicus published a book that would shatter this comfortable cosmic order. The book was called on the revolutions of the celestial spheres, and its central claim was revolutionary and disturbing. Copernicus argued that the Earth was not the center of everything. Instead, he proposed that the Earth and the other planets all orbited around the Sun. Now, you might wonder, why did this matter so much? After all, whether the Earth goes around the Sun or the Sun goes around the Earth, the practical observations from the ground are almost the same. You still see the Sun rise in the east and set in the west. You still see the stars wheel across the night sky. But the implications of this shift were absolutely profound. Think about what it meant psychologically and philosophically. For thousands of years, humans had believed we occupied the central point of creation. We were the purpose of it all. But if Copernicus was right, then Earth was just another planet, orbiting an ordinary star. We weren't at the center. We weren't uniquely important from a cosmic perspective. Our entire sense of cosmic significance had to be reconsidered. The Catholic Church understood these implications very well, which is why they eventually banned Copernicus's book. This wasn't just about astronomy. This was about humanity's place in God's creation. This was about authority and who had the right to determine truth. The resistance to Copernicus's ideas shows just how threatening they were to established worldviews. But truth has a way of refusing to stay buried. In 1609, an Italian scientist named Galileo Galilei pointed a newly invented instrument called a telescope at the sky. What he saw through that crude lens changed everything. He saw mountains and craters on the moon, proving that celestial bodies weren't perfect and unchanging as Aristotle had claimed. He saw spots on the sun, further evidence of celestial imperfection. He saw that Jupiter had its own moons, tiny points of light that clearly orbited the giant planet. This was direct proof that not everything in the cosmos orbited Earth. Galileo also observed the phases of Venus, watching it grow from a thin crescent to nearly full circle, just like the moon goes through phases. This pattern only made sense if Venus orbited the Sun, and we were seeing different portions of its sunlit side as it moved. In the Earth-centered model, Venus should never appear nearly full. These observations provided concrete evidence for Copernicus's model. The telescope wasn't just a tool for looking at things far away. It was a tool that transformed what questions humans could answer about the universe. For the first time, we could see beyond what our naked eyes allowed. We could gather evidence that settled debates that had raged for centuries. And what the telescope revealed was that the universe was far larger, far more complex, and far less centered on us than anyone had imagined. Around the same time, a German astronomer named Johannes Kepler was making his own revolutionary discoveries. Kepler had access to incredibly precise measurements of planetary positions compiled by an astronomer named Tycho Brahe. Kepler believed that mathematical harmony underlay the cosmos, and he spent years trying to find the mathematical patterns in planetary motion. What Kepler discovered was both beautiful and unexpected. The planets didn't move in perfect circles as everyone had assumed. Instead, they moved in ellipses, which are essentially stretch circles. Each planet swept out equal areas in equal times as it orbited, moving faster when closer to the Sun and slower when farther away. And the time it took a planet to complete one orbit was mathematically related to its average distance from the Sun. These patterns, known as Kepler's laws of planetary motion, revealed something profound. The universe operated according to mathematical rules. The cosmos wasn't arbitrary or capricious. It followed laws that humans could discover and express in the language of mathematics. This was an extraordinary insight. It meant that the universe was fundamentally comprehensible. But the true breakthrough came when an Englishman named Isaac Newton asked a deceptively simple question in the 1680s. What force keeps the planets in their elliptical orbits? Why don't they just fly off in straight lines into space? Newton realized something absolutely revolutionary. The same force that makes an apple fall from a tree also keeps the Moon in orbit around Earth and keeps Earth in orbit around the Sun. He called this force gravity. Every object with mass attracts every other object with mass. The strength of this attraction depends on how massive the objects are and how far apart they are. Newton expressed this insight mathematically, creating equations that could predict the motions of planets, moons, comets, and falling apples with remarkable precision. He showed that the same physical laws that govern events on Earth also govern the cosmos. There wasn't one set of rules for the terrestrial realm and another for the celestial realm. There was one set of universal laws. This unification was breathtaking in its implications. It meant that by studying nature here on Earth through experiments, we could understand phenomena happening in the farthest reaches of space. It meant the universe operated like a vast but comprehensible machine, following consistent principles everywhere. Newton's work also raised a new question about the universe's shape and extent. If gravity pulls all masses toward each other, why doesn't the entire universe collapse into one giant clump? Newton's answer was that the universe must be infinite, with matter distributed roughly evenly throughout all of space. In an infinite universe with infinite matter, every point has matter pulling it equally in all directions, so nothing collapses. But this created its own puzzle, which came to be called Olbers' paradox. If the universe is infinite and filled with infinite stars, then no matter which direction you look, your line of sight should eventually hit a star. The entire night sky should be blazing with light as bright as the surface of the sun. Yet when we look up at night, we see mostly darkness punctuated by scattered points of light. Why? This question would haunt astronomers for centuries. The answer would eventually reveal something fundamental about the universe's age and structure. But that answer wouldn't come until the 20th century, when our understanding of the cosmos would undergo yet another revolutionary transformation. The scientists of the 16th and 17th centuries, Copernicus, Galileo, Kepler and Newton, didn't just make discoveries. They established a new way of understanding reality itself. They showed that human beings could uncover the universe's deep structure through observation, experimentation and mathematical reasoning. They proved that the cosmos, despite its vastness and apparent complexity, operated according to laws we could grasp. They displaced Earth from the center of everything, but in doing so, they revealed something perhaps even more remarkable. They revealed that the human mind, this 3-pound organ inside our skulls, could comprehend the architecture of reality itself. Chapter 5. Einstein bends reality. By the year 1900, physicists felt remarkably confident about their understanding of the universe. They had Newton's laws of motion and gravity, which predicted the movements of planets with astonishing accuracy. They had Maxwell's equations, which explained electricity, magnetism, and light as different aspects of the same electromagnetic phenomenon. They had thermodynamics, which explained heat and energy. The universe seemed to be a vast clockwork mechanism, eternal and unchanging, operating according to well-understood mathematical principles. Some prominent scientists even declared that physics was essentially complete, with only minor details left to work out. Then a young patent clerk in Switzerland named Albert Einstein began thinking deeply about some puzzling inconsistencies in the physics of his day, and what he discovered would overturn nearly everything scientists thought they knew about space, time, and gravity. Einstein's insights would ultimately reveal the answer to our central question about the universe's shape, though it would take decades for the full implications to become clear. Einstein's journey began with what seemed like a simple question. Imagine you're on a train moving at constant speed. If you toss a ball straight up, it comes straight back down to your hand, exactly as it would if you were standing still on the ground. From your perspective inside the train, you can't tell whether you're moving or stationary. This principle, that the laws of physics are the same in any reference frame moving at constant velocity, was already well established. It's called the principle of relativity, and Galileo had understood it centuries earlier. But here's where things got strange. Light, according to Maxwell's equations, travels at a specific speed, about 300 million meters per second. But speed relative to what? If you're on a train moving forward and you shine a flashlight forward, does the light move at its normal speed, plus the speed of the train? Common sense says yes, but experiments showed something bizarre. Light always travels at the same speed, regardless of how fast the source is moving. No matter how you measure it, no matter how fast you're going, light always moves at exactly the same velocity. Einstein realized that this created an apparent paradox. How could light have the same speed for everyone, regardless of their motion? The only way this could work was if something we thought was absolute and fixed was actually flexible, and that something was space and time themselves. In 1905, Einstein published his special theory of relativity. He showed that time passes at different rates depending on how fast you're moving. If you travel very fast relative to someone else, your clock runs slower than theirs. Space itself also changes. Objects moving at high speed get compressed in the direction of motion. These aren't optical illusions or measurement errors. Time and space literally behave differently depending on your motion. This was already revolutionary enough. But Einstein wasn't finished. He continued thinking about gravity, and 10 years later, in 1915, he published his general theory of relativity, which revealed something even more extraordinary about the nature of space itself. Let me help you understand Einstein's insight with an image. Imagine you have a large trampoline stretched tight and flat. This represents space. Now place a bowling ball in the center of the trampoline. The heavy ball creates a dip in the fabric, curving it downward. If you now roll a marble across the trampoline near the bowling ball, what happens? The marble doesn't travel in a straight line. Instead, it curves around the bowling ball, following the curved surface of the trampoline. Einstein realized that this is exactly how gravity works. Massive objects like the Sun or Earth don't exert a mysterious force that reaches across empty space to pull on other objects. Instead, massive objects curve the fabric of space-time itself. Other objects then follow the straightest possible paths through this curved space-time, and we perceive that as gravitational attraction. Think about that for a moment. Space is not a fixed, unchanging stage on which events happen. Space itself is dynamic, flexible, capable of being warped and bent by the presence of matter and energy. Time is woven together with space into a four-dimensional fabric called space-time. And this fabric has geometry that can be curved just like the surface of a sphere or a saddle is curved. When light from a distant star passes near the Sun, the light doesn't travel in a perfectly straight line. It follows the curves in space-time created by the Sun's mass, causing the star's apparent position in the sky to shift slightly. In 1919, astronomers observed precisely this effect during a total solar eclipse, providing dramatic confirmation of Einstein's theory. The photograph showed stars appearing in positions they shouldn't occupy, their light bent by the Sun's gravitational influence, just as Einstein had predicted. Einstein's equations of general relativity are beautiful and elegant, but they're also incredibly complex. They describe how matter and energy curve space-time, and how curved space-time tells matter and energy how to move. But here's what makes these equations relevant to our quest to understand the universe's shape. Einstein realized that his equations didn't just describe local curvature around planets and stars. They described the curvature of the entire universe. When Einstein first applied his equations to the cosmos as a whole, he discovered something that disturbed him. His equations predicted that the universe should either be expanding or contracting. It couldn't just sit still. But in 1915, everyone, including Einstein himself, believed the universe was eternal and static, unchanging on cosmic scales. Galaxies might move around a bit, but the overall structure of the cosmos remained constant. To fix this problem, Einstein added an extra term to his equations, something he called the cosmological constant. This was essentially a repulsive force built into the fabric of space itself that could exactly balance gravity and keep the universe static. It was a mathematical trick, but it seemed necessary to make the equations match what everyone believed about the cosmos. But Einstein's equations revealed three fundamental possibilities for the large-scale geometry of the universe. The universe could be positively curved, like the three-dimensional equivalent of the surface of a sphere. In this kind of universe, if you could somehow travel far enough in one direction, you'd eventually return to your starting point, just like traveling around the Earth's surface. Parallel lines would eventually converge and meet. A triangle's angles would add up to more than 180 degrees. This type of universe would have finite volume, though it would have no edge or boundary, just as the surface of a sphere is finite but has no edge. The universe could be negatively curved, like the three-dimensional equivalent of a saddle surface. In this geometry, parallel lines diverge from each other. Triangles have angles that add up to less than 180 degrees. This type of universe would extend infinitely in all directions. Or the universe could be flat, meaning the familiar rules of Euclidean geometry apply on cosmic scales. Parallel lines stay parallel forever. Triangles have angles totaling exactly 180 degrees. This universe could also be infinite, though, as we'll see later, there are some exotic possibilities for how a flat universe could still have finite volume. Which type of universe we live in depends on the overall density of matter and energy in the cosmos. If there's enough mass and energy, gravity will curve space positively. If there's too little, space will be negatively curved, and there's a critical density right in between where space is perfectly flat. Einstein's general relativity transformed our understanding of gravity from a force acting across space to a curvature of space. This theory predicted that the universe has a shape determined by its contents, that space-time is dynamic rather than fixed, and that understanding cosmic geometry requires understanding the distribution of matter and energy throughout the cosmos. But Einstein, like everyone else at the time, still believed the universe was static and eternal. That belief was about to be shattered by observations that would reveal the cosmos to be far more dynamic, far younger, and far stranger than anyone had dared imagine. The static universe Einstein tried to preserve with his cosmological constant didn't exist. And ironically, the cosmological constant he considered his greatest blunder would eventually turn out to describe a real feature of the universe, though not in the way Einstein intended. The stage was now set for the discovery that would revolutionize cosmology and provide the first real clues about the universe's true shape. That discovery would come from a modest telescope on a California mountaintop and an astronomer who would measure the speed of distant galaxies. Chapter 6. The Universe is Running Away. In the 1920s, the world's most powerful telescope sat atop Mount Wilson in California, near Los Angeles. This telescope, with its 100-inch diameter mirror, could gather more light than any previous instrument, allowing astronomers to see farther into space than ever before. And working at this telescope was a man named Edwin Hubble, who would make a discovery so profound that it would completely transform our understanding of the cosmos. But before we get to Hubble's breakthrough, we need to understand the great debate that was raging among astronomers at the time. When you look up at the night sky with the decent telescope, you can see fuzzy, glowing patches scattered among the stars. These nebulae, as they were called, had puzzled astronomers for centuries. Some looked like clouds of gas. Others had beautiful spiral structures. But what were they? One group of astronomers believed these nebulae were clouds of gas and dust within our own Milky Way galaxy. They thought the Milky Way, a vast collection of hundreds of billions of stars, represented essentially the entire universe. Everything we could see belonged to this one grand system. Beyond the Milky Way was just empty space extending forever. Another group had a more radical idea. They proposed that at least some of these nebulae, particularly the spiral ones, were actually separate galaxies, island universes complete unto themselves, lying far beyond the boundaries of the Milky Way. If this were true, the universe was vastly larger than anyone had imagined, filled with countless galaxies scattered through space. The debate came to a head in 1920 when two prominent astronomers held a public discussion at the National Academy of Sciences. Both sides presented their evidence and arguments, but the question couldn't be settled through argumentation alone. What was needed was a definitive measurement of how far away these mysterious spiral nebulae actually were. This is where Hubble made his first major contribution. He found a way to measure enormous cosmic distances using certain types of stars called Cepheid variables. These remarkable stars brighten and dim in a regular, predictable pattern. And here's the crucial discovery that had been made a few years earlier. The period of a Cepheid's variation, how long it takes to go from bright to dim and back to bright again, is directly related to its actual luminosity, how much light it emits. This relationship turns Cepheids into cosmic distance markers. By watching how long a Cepheid takes to vary, you can calculate how intrinsically bright it is. Then, by measuring how bright it appears from Earth, you can figure out how far away it must be. It's the same principle as judging the distance to a light bulb. If you know it's a 100-watt bulb, but it looks very dim, it must be far away. In 1923, Hubble identified Cepheid variables in the Andromeda Nebula, one of the prominent spiral nebulae. When he calculated the distance based on these stars, the result was staggering. Andromeda was approximately 900,000 light-years away. This was far beyond the known size of the Milky Way. Andromeda wasn't a cloud within our galaxy. It was an entirely separate galaxy, comparable in size to the Milky Way itself. The great debate was settled. The spiral nebulae were galaxies, and the universe was incomprehensibly larger than anyone had thought. The Milky Way, vast as it was, represented just one galaxy among countless others scattered through space. Our cosmic perspective had expanded enormously, but Hubble wasn't finished. He had stumbled onto something even more remarkable. As he and other astronomers measured the distances to more and more galaxies, they also analyzed the light coming from those galaxies, and they noticed something very strange about that light. You're probably familiar with the Doppler effect, even if you don't know it by that name. When an ambulance races toward you with its siren blaring, the siren has a high pitch. As the ambulance passes and speeds away, the pitch suddenly drops to a lower tone. This happens because the motion of the ambulance compresses sound waves in front of it, making the wavelength shorter and the pitch higher, while stretching out waves behind it, making the wavelength longer and the pitch lower. Light works the same way. If a light source is moving toward you, its light waves get compressed, shifting toward shorter, bluer wavelengths. If the source is moving away, the waves get stretched, shifting toward longer, redder wavelengths. Astronomers had been using this Doppler shift to measure the speeds of stars for decades. When astronomers examined the light from distant galaxies, they found something astonishing. Nearly all galaxies showed a redshift. Their light was shifted toward longer, redder wavelengths. This meant the galaxies were moving away from us. Not just a few galaxies, but almost every galaxy in every direction. At first, this might seem to suggest that we're at the center of some giant cosmic explosion with everything fleeing from us. But Hubble's careful measurements revealed an even more extraordinary pattern. The farther away a galaxy was, the faster it was moving away from us. And this relationship was remarkably precise. A galaxy twice as far away was moving away twice as fast. A galaxy 3 times as far was moving 3 times as fast. This pattern is exactly what you'd expect if space itself is expanding. Imagine you have a deflated balloon and you draw dots on it with a marker to represent galaxies. Now start inflating the balloon. As the rubber stretches, every dot moves away from every other dot. And here's the key insight. From the perspective of any dot, all the other dots are moving away, with farther dots moving away faster. There's no center to this expansion. Every point sees the same pattern. This is what Hubble had discovered. The universe is expanding. Galaxies aren't moving through static space. Space itself is growing, carrying galaxies along with it like raisins in a rising loaf of bread. This discovery, published in 1929, completely overturned the static universe that Einstein and everyone else had believed in. Einstein reportedly called the cosmological constant he'd added to his equations his greatest blunder. If he'd trusted his original equations, he could have predicted the expansion of the universe before it was observed. But no one, not even Einstein, had been bold enough to imagine such a dynamic cosmos. The expansion of the universe had profound implications. If the universe is expanding now, getting larger with every passing moment, that means it was smaller in the past. If you imagine running the expansion backward like a film in reverse, galaxies get closer and closer together. The universe becomes denser and denser, hotter and hotter. Run the clock far enough backward and you reach a point where all the matter and energy in the universe was compressed into an incredibly small, incredibly hot state. This led to an inescapable conclusion. The universe had a beginning. It wasn't eternal and unchanging. At some point in the finite past, the universe began in an event of unimaginable energy and density. An event that would eventually be called the Big Bang. This realization changed everything. It meant the universe has a history. It has evolved and changed over time. The cosmos we see today is very different from the cosmos of the distant past, and will be very different in the future. Understanding the shape of the universe now required understanding its entire history, from the moment of its birth to the present day and beyond. Hubble's discovery of cosmic expansion gave scientists their first real tool for understanding the universe's shape. The rate of expansion and the total amount of matter in the universe would determine whether space curves positively, negatively, or remains flat. The quest to measure these quantities would occupy cosmologists for decades to come. But first, scientists needed to understand what actually happened at the beginning of time, in those first unimaginable moments when the entire observable universe was smaller than an atom. They needed to understand the Big Bang itself. Chapter 7. The Birth of Everything. Let me take you back to the very beginning. Not the beginning of your life, not the beginning of human civilization, not even the beginning of the earth or the sun. I want to take you back to the beginning of everything, the beginning of time itself, the beginning of space, the moment when the universe burst into existence. This is where our story becomes truly extraordinary, because we're going to discuss events that happened 13.8 billion years ago, events that lasted mere fractions of a second, events so extreme that they challenge the very limits of human comprehension. Yet, through brilliant detective work, careful observation, and deep mathematical reasoning, scientists have managed to piece together what happened in those first moments with remarkable confidence. The idea that the universe had a beginning was actually proposed before Hubble's discovery of cosmic expansion. In 1927, a Belgian priest and physicist named Georges Lemaitre independently derived solutions to Einstein's equations that suggested the universe was expanding. Working backward, Lemaitre proposed that the universe began from what he called the primeval atom, a cosmic egg that contained all the matter and energy that would ever exist, compressed into an infinitesimally small point. When Hubble's observations confirmed that the universe was indeed expanding, Lemaitre's idea gained credibility. But many scientists resisted it fiercely. The British astronomer Fred Hoyle was particularly skeptical. During a radio broadcast in 1949, Hoyle mockingly referred to Lemaitre's idea as the Big Bang theory. The name was meant to be dismissive, to make the concept sound absurd, but the name stuck. And ironically, the Big Bang became one of the most successful scientific theories ever developed. Why did scientists resist the Big Bang idea? For some, it was because the concept sounded too much like religious creation stories. Science was supposed to explain the universe in purely naturalistic terms, without need for a creator or a moment of creation. An eternal universe seemed more scientifically respectable. For others, the resistance was simply because the idea was so strange and unprecedented. The universe having a definite beginning, an edge to time itself, was difficult to accept. But let's be very clear about what the Big Bang actually was, because many people misunderstand it. The Big Bang was not an explosion of matter into empty space. It was not like a bomb going off, sending debris flying outward into a pre-existing void. Rather, the Big Bang was the explosive expansion of space itself. It happened everywhere at once. There was no outside. There was no before in any conventional sense. Try to wrap your mind around this. At the moment of the Big Bang, the entire observable universe, everything we can see with our most powerful telescopes, all the galaxies and stars and planets, was compressed into a region far smaller than a single atom. In fact, the very early universe was infinitesimally small, possibly even a mathematical point with zero size. But this point wasn't sitting somewhere in empty space. This point was space, all of space. When the Big Bang happened, space itself began expanding, and it's been expanding ever since. The galaxies aren't flying away from each other through space. They're being carried apart by the expansion of the space between them. Let me walk you through what scientists believe happened in those first unimaginable moments, based on our best understanding of physics. At the very beginning, at time zero, all of physics as we know it breaks down. Our equations produce infinities and nonsensical results. We simply don't have a theory that can describe what happened at the absolute instant of creation. To understand that moment, we'd need a theory of quantum gravity, something that unifies quantum mechanics with general relativity, and we don't yet have such a theory. But we can describe what happened a tiny fraction of a second after the beginning. And when I say tiny fraction, I mean incomprehensibly small. At about 1 × 10⁻⁻36 seconds after the Big Bang, something remarkable happened. The universe underwent a period of inflation. During inflation, space expanded faster than the speed of light. Now, you might object that Einstein's relativity says nothing can travel faster than light. That's true for objects moving through space. But space itself can expand at any rate. During inflation, the universe grew by an enormous factor in an incredibly brief time. Something the size of an atom expanded to something the size of a grapefruit in a tiny fraction of a second. This might sound like wild speculation, but inflation theory actually solves several major puzzles about the universe we observe. It explains why the universe appears so uniform in all directions. It explains why space appears to be flat rather than curved. And it explains where the tiny density variations came from that eventually grew into galaxies and stars. After inflation ended, the universe was filled with incredible amounts of energy. The temperature was so high that matter as we know it couldn't exist. There were no atoms, no protons, no neutrons. There was just pure energy in the form of radiation and exotic particles. The universe at this point was like the inside of a star, but millions of times hotter. As the universe continued expanding, it cooled. This is a crucial point. Expansion causes cooling. When you let air out of a pressurized tire, the air gets cold. The same principle applies to the universe. As space expanded, the energy density decreased and the temperature dropped. When the temperature dropped below about 1 trillion degrees, a phase transition occurred. Energy began condensing into the fundamental particles that make up ordinary matter. Quarks and electrons appeared. The universe was still far too hot for these particles to combine into atoms, but the building blocks of matter now existed. During the first few minutes after the Big Bang, nuclear fusion occurred throughout the entire universe. Protons and neutrons slammed together with such energy that they fused into helium nuclei. This primordial nucleosynthesis lasted only about 15 minutes, but it was crucially important. By the time it was over, about 75% of ordinary matter was hydrogen and about 25% was helium, with tiny traces of lithium and other light elements. This predicted ratio of hydrogen to helium is one of the major triumphs of Big Bang theory. When astronomers measure the ratio of hydrogen to helium in the oldest stars and gas clouds, they find exactly the proportions predicted by the theory. The universe really did go through this hot, dense phase where nuclear fusion occurred everywhere. But even after nuclear fusion ended, the universe was still far too hot for atoms to form. For the next 380,000 years, the universe was filled with a hot plasma of electrons and atomic nuclei. Light couldn't travel freely through this plasma. Any photon of light that tried to go somewhere would immediately collide with an electron and get scattered in a random direction. The universe was opaque, like being inside a thick fog. Then, when the universe was about 380,000 years old, something momentous happened. The temperature had finally dropped enough for electrons to combine with atomic nuclei and form stable atoms. Mostly hydrogen atoms, some helium atoms. This is called recombination, and it changed everything. Once atoms formed, light could finally travel freely. The photons that had been constantly scattering off free electrons were suddenly able to stream through space, unimpeded. The universe became transparent. And those photons that were released at the moment of recombination have been traveling through space ever since, carrying information about what the universe was like when it was just 380,000 years old. This is the oldest light we can possibly see. We call it the cosmic microwave background radiation. It's a snapshot of the universe when it was 1,000 times smaller and hotter than it is today. And it's still out there, all around us, waiting to be detected by anyone who has the right instruments to see it. The discovery of this cosmic microwave background radiation, which we'll discuss in detail in the next chapter, provided the smoking gun evidence that the Big Bang really happened. It confirmed that the universe had a hot, dense beginning and has been expanding and cooling ever since. It gave cosmologists a powerful tool for measuring the properties of the universe, including its shape. The story of the Big Bang shows us that the universe has a history, a narrative arc from an incredibly hot and dense state to the cool, diffuse cosmos we see today. The shape of the universe is intimately connected to this history. The density of matter and energy determined how gravity would curve space, and the early moments of inflation may have determined whether that curvature would be positive, negative, or flat. Understanding where we came from is essential to understanding where we are and where we're going. Chapter 8. Evidence written in light. In the year 1964, two engineers working at Bell Telephone Laboratories in New Jersey were trying to solve an annoying technical problem. Arno Penzias and Robert Wilson were testing a large horn-shaped radio antenna that was meant to receive signals bounced off satellites. But no matter what they did, they couldn't get rid of a persistent background hiss in their data. This static was ruining their measurements, and they couldn't figure out where it was coming from. The two engineers were thorough and methodical. They checked all their equipment. They looked for sources of radio interference from nearby New York City. They even noticed that pigeons had been roosting inside the antenna, leaving droppings everywhere. Maybe the pigeon waste was somehow generating radio signals. They carefully cleaned out the antenna, removing all the bird droppings, but the mysterious hiss remained. What made this signal so puzzling was its character. It came from every direction in the sky with almost exactly the same intensity. It didn't matter where they pointed the antenna. North, south, east, west, up, down, the signal was always there, always the same. And it had a very specific character, corresponding to radiation from something with a temperature of about 3 degrees above absolute zero. 3 degrees Kelvin, as physicists say. Penzias and Wilson had no idea what they'd found. They were engineers, not cosmologists. They just wanted to get rid of the noise so they could do their actual work. But through a series of conversations and coincidences, word of their mysterious signal reached a team of physicists at nearby Princeton University who immediately understood what it was. These Princeton physicists, led by Robert Dicke, had actually been building their own radio telescope to search for exactly this kind of signal. They'd realized that if the Big Bang theory was correct, if the universe really had been incredibly hot and dense in the distant past, then there should still be radiation left over from that early state. Let me explain why. Remember that for the first 380,000 years after the Big Bang, the universe was filled with hot plasma, and light couldn't travel freely. Photons kept bouncing off electrons, but when atoms formed and the universe became transparent, all those photons were suddenly released. They streamed freely through space in all directions. And those photons are still traveling through space today, carrying information from the infant universe. But here's the crucial point. The universe has been expanding since those photons were released. And as space expands, it stretches out the wavelengths of light traveling through it. Light that started out as visible or ultraviolet radiation has been stretched by cosmic expansion into longer and longer wavelengths. After 13.8 billion years of expansion, that ancient light has been stretched all the way into microwave wavelengths. This is why we call it the cosmic microwave background, or CMB for short. It's microwave radiation that comes from every direction in space, representing the afterglow of the Big Bang itself. It's the oldest light in the universe, a baby picture of the cosmos, when it was less than 1/400,000th of its current age. What Penzias and Wilson had accidentally discovered was precisely this cosmic microwave background. They'd found the smoking gun evidence for the Big Bang, the proof that the universe really had gone through a hot, dense phase. They'd detected light that had been traveling through space for over 13 billion years. Light that was created when the universe was 1,000 times smaller than it is today. This discovery was so important that Penzias and Wilson won the Nobel Prize in Physics in 1978. And it's somewhat ironic that they won for something they'd initially viewed as an annoyance, a source of noise they wanted to eliminate. They were looking for pigeons and radio interference, and instead they found the echo of creation itself. But the cosmic microwave background turned out to be far more than just confirmation that the Big Bang happened. It became one of the most powerful tools cosmologists have for understanding the universe's properties, including its shape. Let me explain why this ancient light is so incredibly valuable. When we observe the cosmic microwave background with sensitive instruments, we find that it's not perfectly uniform. The temperature is about 2.7 degrees Kelvin in every direction, but there are tiny variations from point to point. In one direction, the temperature might be 2.725 degrees. In another direction, it might be 2.695 degrees. These variations are incredibly small, only about 1 part in 100,000. But they're real, and they're extraordinarily important. These tiny temperature variations represent density variations in the early universe. Places that were slightly hotter had slightly more matter and energy. Places that were slightly cooler had slightly less. These variations were the seeds that eventually grew into all the cosmic structure we see today. The slightly denser regions had a bit more gravity, so they pulled in more matter. Over hundreds of millions of years, these small overdensities grew into galaxies, stars, planets, and eventually people. The pattern of these variations, their characteristic size and distribution, tells us tremendous amounts about the universe. It tells us how old the universe is. It tells us how fast it's expanding. It tells us the density of ordinary matter, and dark energy. And crucially, it tells us the geometry of space itself. Here's how it works. Sound waves in the early universe created characteristic patterns in the density of matter. Just like sound waves in air create regions of compression and rarefaction, pressure and gravity in the early universe created ripples in the distribution of matter and energy. These ripples left their imprint on the cosmic microwave background. Now, the size of these ripples in the CMB depends on the geometry of space. In a flat universe, these patterns appear a certain size in the sky. In a positively curved universe, they'd appear larger. In a negatively curved universe, they'd appear smaller. It's like drawing circles on different surfaces. A circle drawn on a flat sheet of paper has a certain diameter. The same circle drawn on the surface of a sphere would appear to have a different size if you measured it along the curved surface. In 1989, NASA launched a satellite called the Cosmic Background Explorer, or COBE. This satellite made the first detailed measurements of the cosmic microwave background from space above the interference of Earth's atmosphere. COBE confirmed that the radiation had exactly the spectrum expected from the Big Bang and detected the tiny temperature variations for the first time. The principal scientists on COBE, John Mather and George Smoot, won the Nobel Prize for this work. When Smoot announced COBE's findings at a scientific conference, he said the team had seen the face of God. What he meant was that they'd seen the structure imprinted on the universe at the moment of creation, the initial conditions from which everything else flowed. But COBE was just the beginning. In 2001, NASA launched a much more sophisticated satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP. This spacecraft measured the cosmic microwave background with far greater precision and resolution than COBE. It created detailed maps showing the tiny temperature variations across the entire sky. The WMAP data allowed cosmologists to measure cosmic properties with unprecedented accuracy. They could determine the age of the universe to within 1%. They could measure the density of different components of the universe, and they could determine the geometry of space with remarkable precision. Then, in 2009, the European Space Agency launched the Planck satellite, the most sensitive CMB observatory ever built. Planck measured the cosmic microwave background with exquisite detail, determining properties of the universe to better than 1% accuracy in many cases. What did all these observations reveal about the shape of the universe? The answer was flat. When scientists measured the characteristic size of the patterns in the CMB and compared them to predictions for different geometries, they found that space is flat to within less than 0.5% margin of error. The angles of cosmic triangles add up to exactly 180 degrees. Parallel lines stay parallel forever. The universe has the geometry that Euclid described for flat space, at least on the largest scales we can measure. This was a remarkable discovery. Remember that Einstein's equations allowed three possibilities: positively curved like a sphere, negatively curved like a saddle, or perfectly flat. And the universe turned out to be almost exactly flat. This isn't a coincidence. As we'll discuss later, the flatness of the universe provides strong evidence for cosmic inflation, the brief period of rapid expansion in the first moments after the Big Bang. The cosmic microwave background also revealed other crucial information. It showed that the universe is composed of about 5% ordinary matter, the stuff that makes up atoms, stars, and planets. About 27% is dark matter, a mysterious form of matter that doesn't emit light, but exerts gravitational influence. And about 68% is dark energy, an even more mysterious component that's causing the universe's expansion to accelerate. These observations from the cosmic microwave background represent an extraordinary triumph of human ingenuity. We've taken light that's been traveling for 13.8 billion years and used it to reconstruct what the universe was like when it was less than 400,000 years old. We've measured the geometry of space itself. We've determined the composition of the cosmos, and we've confirmed in remarkable detail the story of the universe's evolution from the Big Bang to the present day. What started as an annoying hiss in a radio antenna became a window into the birth of the universe and a tool for measuring cosmic geometry. The cosmic microwave background is perhaps the single most important observational resource in cosmology. It's a fossil from the early universe, perfectly preserved in the form of ancient light that surrounds us on all sides. Every time you turn on an old television set and see static on an unused channel, about 1% of that static is actually cosmic microwave background radiation. You're seeing the echo of the Big Bang itself. Chapter 9. The critical density. Now we need to talk about a number that determines the ultimate fate of everything that exists. This number goes by the Greek letter omega, and it represents something absolutely fundamental about the universe. Omega describes the density of the universe compared to a special value called the critical density. And whether omega is greater than 1, less than 1, or exactly equal to 1, determines whether the universe is positively curved, negatively curved, or flat. It also determines whether the universe will expand forever or eventually collapse back on itself. Let me help you understand what density means in a cosmic context. When we talk about the density of the universe, we're asking how much stuff, how much matter and energy exists in a given volume of space. On Earth, you're used to thinking about density in terms of how heavy something is for its size. Lead is denser than wood because the same volume of lead contains more mass. The universe has an average density that we can calculate by adding up all the matter and energy in a large region of space and dividing by the volume of that region. Now, you might think the universe's density would be straightforward to measure. Just count up all the galaxies, stars and gas in a region of space and calculate the density. But it's not that simple, as we'll discover when we talk about dark matter and dark energy. There's far more to the universe than what we can see with our telescopes. Here's where critical density comes in. Einstein's equations of general relativity relate the curvature of space to the density of matter and energy. And these equations reveal something remarkable. There's a special density value where space is exactly flat, perfectly balanced between positive and negative curvature. This is the critical density. If the actual density of the universe is greater than the critical density, then there's enough matter and energy for gravity to curve space positively. The universe would be like the surface of a sphere, finite in volume, with geometry where parallel lines eventually meet. In this type of universe, gravity is strong enough that the expansion from the Big Bang will eventually slow down, stop, and reverse. The universe will collapse back on itself in what's sometimes called the Big Crunch, the opposite of the Big Bang. If the actual density is less than the critical density, then there's not enough matter and energy to curve space positively. Instead, space curves negatively like a saddle surface. This universe is infinite in extent, and its expansion will continue forever, accelerating even, with galaxies moving farther and farther apart throughout eternity. And if the density is exactly equal to the critical density, then space is flat. The universe sits precisely balanced between the two extremes. In this case, the universe will also expand forever, but the expansion gradually slows down, approaching but never quite reaching a standstill. Now, here's something that puzzled cosmologists for decades. When they tried to measure omega by counting up all the visible matter in the universe, all the stars and gas they could detect, they got a value of only about 0.05. This suggested the universe was nowhere near the critical density. It should be negatively curved and expanding forever at an accelerating rate. But there was a problem with this conclusion, a problem that became increasingly obvious as measurements improved. The problem is called the flatness problem, and it's one of the most remarkable fine-tuning puzzles in all of cosmology. Here's the issue. If the universe started out with omega significantly different from 1, then that difference would have grown enormously over time. Let me give you an analogy. Imagine you're trying to balance a pencil on its tip. If the pencil is tilted even slightly away from perfectly vertical, it will fall over almost immediately. The initial tilt gets amplified very quickly. The same thing happens with omega. If omega was slightly greater than 1 in the early universe, then gravity would have caused the universe to collapse very quickly, perhaps in just a few thousand years. If omega was slightly less than 1, the universe would have expanded so rapidly that galaxies and stars never could have formed. For omega to be anywhere close to 1 today, it must have been extraordinarily close to 1 in the very early universe. How close? Calculations show that at 1 second after the Big Bang, omega must have been equal to 1 to within 1 part in a million billion. At even earlier times, the fine-tuning is even more extreme. This seems like an incredible coincidence. Why would the universe start out with density so exquisitely fine-tuned to the critical value? This is where the theory of cosmic inflation comes to the rescue. Remember that inflation is the idea that the universe underwent a brief period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. During inflation, space expanded faster than the speed of light, growing by an enormous factor in an incomprehensibly brief time. Here's the beautiful thing about inflation. No matter what curvature space started with, inflation would have flattened it out. Think about the surface of a balloon. When the balloon is small, you can easily see that its surface is curved. But as you inflate the balloon to enormous size, any small region of its surface appears flatter and flatter. If you inflated the balloon to the size of the Earth, the curvature would be essentially undetectable on human scales. Cosmic inflation does the same thing to the geometry of the universe. It predicts that after inflation, omega should be extraordinarily close to 1. Space should be almost perfectly flat, at least in the region we can observe. This prediction is one of the major successes of inflation theory. It explains the flatness problem naturally. But inflation makes an even more specific prediction. It suggests that omega shouldn't just be close to 1, it should be extremely close to 1. So close that detecting any deviation from perfect flatness would be nearly impossible with current technology. The universe should be flat to within a tiny fraction of a percent. And this is exactly what observations show. When scientists measured the geometry of space using the cosmic microwave background and other methods, they found that omega is indeed very close to 1. The most recent measurements from the Planck satellite indicate that omega is between 0.996 and 1.004 with 99.6% confidence. In other words, as far as we can measure, the universe is perfectly flat. This agreement between inflation's prediction and actual observations is one of the reasons scientists have confidence in inflation theory, despite the fact that it describes events that happened in the first tiny fraction of a second after the Big Bang, events we can never directly observe. But here's something important to understand. When we say omega equals 1 and the universe is flat, we're talking about the total density of everything in the universe, not just the ordinary matter we can see. And, as we're about to discover, The vast majority of the universe consists of things we cannot see directly. Things that don't emit light, don't absorb light, don't interact with light at all. To understand what omega really means and what the universe is made of, we need to talk about the invisible components of the cosmos. We need to talk about dark matter and dark energy. The critical density, omega, and the flatness of space are all intimately connected. They tell us that we live in a universe that sits balanced on a knife edge between different possible fates. And that balance, that fine-tuning, points toward dramatic events in the first moments of cosmic history that shaped everything that came after. Chapter 10. The Invisible Universe. In the 1970s, an astronomer named Vera Rubin was doing something that seemed fairly routine. She was measuring how fast stars orbit within galaxies. This is the kind of careful, detailed observational work that forms the foundation of astronomy. It's not glamorous, but it's essential. Rubin pointed her telescope at spiral galaxies and measured the velocities of stars at different distances from the galactic center. What she expected to find was straightforward. Stars near the center of a galaxy should orbit quickly because there's a lot of mass nearby, pulling them with strong gravity. Stars far from the center should orbit more slowly because most of the galaxy's mass is concentrated toward the middle. This is exactly how the solar system works. Mercury orbits the Sun very quickly because it's close. Neptune orbits very slowly because it's far away. But when Rubin analyzed her data, she found something completely unexpected. Stars at the edges of galaxies were orbiting just as fast as stars near the center. In some cases, stars on the outer edges were moving even faster than they should based on the visible matter in the galaxy. This made absolutely no sense according to Newton's laws of gravity. In fact, the outer stars were moving so fast that they should have escaped the galaxy's gravity entirely. They should have been flung out into intergalactic space like a stone released from a sling. Yet there they were, happily orbiting along as if held by some invisible gravitational force. Rubin's observations created a crisis in astronomy. Either Newton's laws of gravity, which had worked perfectly for 300 years, were wrong on galactic scales, or there was far more matter in galaxies than we could see with our telescopes. Some kind of invisible mass must be providing the extra gravity needed to keep those outer stars in orbit. This invisible matter came to be called dark matter. And I want to be very clear about what dark means in this context. It doesn't mean the matter is black or obscured by dust. It means this matter doesn't interact with light at all. It doesn't emit light. It doesn't absorb light. It doesn't reflect or scatter light. Light passes right through it as if it weren't there. The only way we know dark matter exists is through its gravitational effects on things we can see. At first, astronomers wondered if dark matter might just be ordinary matter that happens to be dark. Maybe it was planets or black holes or clouds of cold gas, things made of normal atoms but not bright enough to see. But as evidence accumulated, it became clear that dark matter couldn't be ordinary matter at all. It had to be something fundamentally different, made of particles we've never directly detected. How do we know this? Several lines of evidence all point to the same conclusion. First, the amount of helium created in the Big Bang depends on how many ordinary atoms existed in the early universe. The observed helium abundance tells us that ordinary matter can account for only about 5% of the critical density. But the gravitational effects we observe require much more matter than this. Second, we can actually see dark matter's gravitational effects directly through a phenomenon called gravitational lensing. Remember that mass curves space-time, and light follows those curves. When light from a distant galaxy passes near a massive cluster of dark matter, the light gets bent and distorted. We see the background galaxy stretched into arcs or even multiple images, like looking through a cosmic magnifying glass. By studying these lensing patterns, astronomers can map out where dark matter is located, even though they can't see the dark matter itself. And what they find is that dark matter forms vast halos around galaxies, extending far beyond the visible stars. In fact, there's roughly 5 times as much dark matter as ordinary matter in the universe. The cosmic microwave background provides even more evidence. The pattern of tiny temperature variations in the CMB depends on the balance between ordinary matter and dark matter in the early universe. When cosmologists analyze this pattern in detail, they find clear signatures of dark matter gravitationally amplifying the density variations that eventually grew into galaxies. So what is dark matter? The honest answer is, we don't know for certain. But the leading hypothesis is that dark matter consists of exotic particles left over from the Big Bang. These particles would interact very weakly with ordinary matter, passing through atoms like ghosts, affecting things only through gravity. Physicists have proposed several candidates. One possibility is particles called WIMPs, which stands for weakly interacting massive particles. These would be heavy particles that rarely interact with ordinary matter. Another possibility involves a different type of particle called axions, which would be extremely light but incredibly numerous. Scientists have built elaborate experiments deep underground, shielded from cosmic rays and other interference, trying to detect the rare occasions when a dark matter particle might collide with an ordinary atom. So far, these experiments haven't definitively detected dark matter particles, but the search continues. Finding out what dark matter is made of remains one of the biggest open questions in physics. But as mysterious as dark matter is, there's something even stranger lurking in the universe. Something that makes up more than twice as much of the cosmos as dark matter does. Something that's causing the expansion of the universe to accelerate, even though gravity should be slowing it down. This component is called dark energy, and it's one of the most profound mysteries in all of science. In the late 1990s, 2 separate teams of astronomers set out to measure how much cosmic expansion was slowing down due to gravity. The question seemed straightforward. We know the universe is expanding. We know that gravity from all the matter in the universe should be gradually slowing that expansion. By measuring exactly how much the expansion has slowed down over cosmic history, we can determine how much matter the universe contains. To make this measurement, the teams used Type Ia supernovae as cosmic distance markers. These exploding stars all have roughly the same intrinsic brightness, so by measuring how bright they appear from Earth, you can calculate how far away they are. And by measuring their redshift, you can determine how fast they were receding when they exploded. This tells you the expansion rate of the universe at different times in cosmic history. Both teams expected to find that expansion was slowing down. The only question was how much it was slowing. Would the universe expand forever, or would gravity eventually halt the expansion and cause a collapse? The teams competed to be first to answer this question, checking and rechecking their data to make sure everything was correct. And then they got a result that left them absolutely stunned. The universe wasn't slowing down at all. It was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if expansion had been slowing down. Somehow, cosmic expansion was accelerating. This discovery earned the team leaders the Nobel Prize in Physics in 2011. But winning the prize didn't mean they understood what they'd found. To this day, the acceleration of cosmic expansion remains deeply mysterious. What could cause expansion to accelerate? It requires something with repulsive gravity, something that pushes space apart rather than pulling it together. And this something has to fill all of space, not just clump in galaxies like ordinary matter and dark matter do. Cosmologists call this mysterious component dark energy. The simplest explanation for dark energy is that it represents energy inherent in space itself. Empty space, the vacuum, might have energy associated with it. And according to Einstein's equations, vacuum energy creates a kind of negative pressure that causes space to expand faster and faster. Ironically, this is exactly what Einstein's cosmological constant represented. Remember that Einstein added this constant to his equations to keep the universe static, then called it his greatest blunder when expansion was discovered. But it turns out Einstein's cosmological constant, reinterpreted as vacuum energy, provides a perfect mathematical description of dark energy. The problem is that when physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer that's wrong by a factor of about 10 to the power of 120. That's one followed by 120 zeros. It's the worst prediction in the history of science. Something is clearly missing from our understanding of how quantum mechanics and gravity fit together. When we add up everything in the universe based on our best current measurements, here's what we find. About 68% of the total energy density is dark energy. About 27% is dark matter. And only about 5% is ordinary matter, the stuff that makes up atoms, stars, galaxies, planets and people. Everything you've ever seen, everything you've ever touched, every atom in your body represents only 5% of what exists. This means that 95% of the universe is invisible to us. We live in a cosmos dominated by components we don't fully understand. Dark matter and dark energy are two of the greatest mysteries in science. We know they exist because of their effects, but we don't know what they fundamentally are. Yet these mysterious components are absolutely crucial for understanding the shape and fate of the universe. Dark matter contributes to omega, helping determine whether space is positively curved, negatively curved, or flat. Dark energy dominates the universe's total energy budget and determines how fast expansion accelerates. Together, they control the ultimate destiny of everything that exists. The discovery that most of the universe is invisible, that we can directly observe only a tiny fraction of what's out there, is humbling. It reminds us that despite all we've learned, we still have tremendous amounts left to discover. The universe is far stranger and more mysterious than it appears at first glance. Chapter 11. The universe is accelerating. Let me take you back to the late 1990s, to a moment when two teams of astronomers thought they were about to answer a straightforward question. They were competitors, racing each other to measure something that seemed simple in principle. They wanted to know how much the expansion of the universe had slowed down over cosmic time. Both teams were confident they'd find evidence of deceleration. After all, gravity pulls everything together, so cosmic expansion should be gradually slowing down, right? What these teams discovered instead would overturn our understanding of the cosmos and reveal that the universe is even stranger than anyone had imagined. Their discovery would show that the universe isn't just expanding, it's expanding faster and faster with each passing moment. Something invisible and mysterious is pushing the entire fabric of space apart at an accelerating rate. The two teams were called the Supernova Cosmology Project and the High Z Supernova Search Team. The leaders of these groups were brilliant scientists named Saul Perlmutter, Brian Schmidt, and Adam Rees. They were using the most powerful telescopes available, sophisticated cameras, and careful analysis techniques, and they were focused on a particular type of cosmic event called a Type Ia supernova. Let me explain what makes Type Ia supernova so useful for cosmology. These explosions happen when a white dwarf star, the dense remnant of a star like our Sun, accumulates matter from a companion star. When the white dwarf's mass reaches a very specific limit, about 1.4 times the mass of our Sun, it can no longer support itself and collapses catastrophically. The collapse triggers runaway nuclear fusion, and the entire star explodes in a supernova. Here's the crucial point. Because Type Ia supernova always occur at the same mass limit, they always release roughly the same amount of energy. This means they all reach approximately the same peak brightness. Astronomers call them standard candles, cosmic light bulbs that all shine with the same intrinsic luminosity. Why is this useful? Imagine you're looking at streetlights at night. If you know that all the streetlights are 100-watt bulbs, then you can judge their distance by how bright they appear. A dim streetlight is farther away than a bright one. The same principle works with Type Ia supernovae. By measuring how bright they appear from Earth and comparing that to their known intrinsic brightness, you can calculate exactly how far away they are. But distance alone isn't enough to measure cosmic expansion. You also need to know how fast each supernova is moving away from us. And this is where redshift comes in. Remember that light from objects moving away gets stretched to longer, redder wavelengths. By measuring how much the light from a supernova has been redshifted, you can determine its recession velocity. Now, here's where it gets interesting. When you combine distance and recession velocity for many supernovae at different distances, you can reconstruct the expansion history of the universe. Distant supernovae show you what expansion was like billions of years ago, because their light has been traveling for billions of years to reach us. Nearby supernovae show you what expansion is like more recently. If expansion were slowing down due to gravity, distant supernovae should appear slightly brighter than expected, because they'd be closer than they would be if expansion had remained constant. Think about it this way. If you've been decelerating, you haven't travelled as far as you would have at constant speed, so you're closer to your starting point. Both teams spent years gathering data on dozens of Type Ia supernovae across a wide range of distances. They developed sophisticated techniques to find these rare explosions, to measure their brightness accurately, and to account for various sources of error. This was painstaking work requiring hundreds of nights at telescopes around the world, and then came the moment of truth. When both teams independently analyzed their data, they found something nobody expected. The distant supernovae were dimmer than predicted, not brighter, dimmer. This meant they were farther away than they should be if expansion had been constant or slowing down. There was only one possible explanation. Expansion must be accelerating. The universe is growing faster now than it was billions of years ago. Something is actively pushing space apart, counteracting gravity and causing cosmic acceleration. At first, both teams thought they'd made a mistake. They checked their data obsessively. They looked for every possible source of error. Could dust between us and the supernovae be dimming their light? Could the distant supernovae be intrinsically dimmer than nearby ones for some reason? Could the observations somehow be wrong? But the more they checked, the more confident they became. The effect was real. Both teams were seeing the same thing independently. The universe's expansion is accelerating. In 1998, both teams published their results, and the scientific world was shocked. Think about how counterintuitive this is. Imagine throwing a ball up into the air. Gravity pulls it down, slowing its upward motion until it stops and falls back. Now imagine throwing a ball upward and watching it go faster and faster as it rises, accelerating away from you despite gravity trying to pull it back. That's essentially what the universe is doing. Despite all the matter in the cosmos pulling inward through gravity, space itself is expanding at an ever-increasing rate. What could possibly cause this? The answer requires something with properties unlike anything we encounter in everyday life. This mysterious component needs to have negative pressure. It needs to push outward rather than pull inward. And it needs to fill all of space uniformly rather than clumping into galaxies and clusters like ordinary matter does. Physicists and cosmologists call this mysterious component dark energy, though that name doesn't really explain what it is. The word dark here means invisible and unknown, just like with dark matter, but dark energy is completely different from dark matter in its properties and effects. The simplest mathematical description of dark energy is Einstein's cosmological constant. Remember that Einstein originally added this constant to his equations to keep the universe static, then abandoned it when Hubble discovered cosmic expansion. Einstein reportedly called the cosmological constant his greatest blunder. But it turns out that something very much like the cosmological constant actually exists in nature. In this interpretation, dark energy represents the energy of empty space itself, what physicists call vacuum energy. According to quantum mechanics, even completely empty space isn't truly empty. Virtual particles constantly pop into existence in particle and antiparticle pairs, exist for a brief moment, then annihilate each other. This quantum activity gives the vacuum an intrinsic energy density. And here's the weird part. Vacuum energy has a very peculiar property. As space expands and more vacuum is created, the total amount of vacuum energy increases. Unlike matter, which gets diluted as space expands, vacuum energy maintains constant density. And this vacuum energy creates a repulsive gravitational effect, a negative pressure that pushes space apart. The mathematics works beautifully. A cosmological constant acting as vacuum energy produces exactly the kind of cosmic acceleration that observations show. It explains why expansion is speeding up rather than slowing down. It explains why this effect is becoming more and more dominant over time. But there's a huge problem. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's absurdly wrong. The calculation predicts a vacuum energy density about 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. It's the most spectacularly incorrect prediction in the history of physics. This enormous discrepancy between theory and observation is called the cosmological constant problem, and it remains one of the deepest unsolved mysteries in fundamental physics. We know dark energy exists. We can measure its effects with great precision, but we have no good explanation for why it has the value it does or what it fundamentally is. Some physicists have proposed that dark energy might not be a cosmological constant at all. Maybe it's a dynamic field that changes over time, something called quintessence. Maybe the laws of gravity need to be modified on cosmic scales. Maybe we're completely misunderstanding something fundamental about how the universe works. All these ideas are being actively investigated, but so far none has proven more successful than the simple cosmological constant model. What we do know from observations is that dark energy makes up about 68% of the total energy budget of the universe. It's the single largest component of the cosmos. Dark matter accounts for about 27%. And ordinary matter, everything made of atoms, including stars, planets and people, represents only about 5% of the total. This means that more than 95% of the universe consists of components we don't fully understand. We can measure their effects with great precision. We can determine how much of each there is. but we don't know what they fundamentally are or why they have the properties they do. The discovery of cosmic acceleration has profound implications for the universe's ultimate fate. In the distant future, assuming dark energy continues to behave as it does now, the universe will expand ever faster. Galaxies beyond our local group will eventually recede from us faster than light can travel, disappearing beyond a cosmic horizon. Billions of years from now, observers in the Milky Way will see a universe that appears empty except for our own local cluster of galaxies. Eventually, trillions of years in the future, even atoms might be torn apart by the accelerating expansion in what's sometimes called the Big Rip, though this depends on the exact nature of dark energy. Or, if dark energy remains constant, the universe will simply expand forever, becoming ever colder, ever emptier, approaching a state of maximum entropy called heat death. The discovery that the universe's expansion is accelerating, that dark energy dominates the cosmos, earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Their work revealed that we live in a universe stranger than we imagined, a universe where most of what exists remains profoundly mysterious. And this discovery is directly relevant to our quest to understand the universe's shape. Dark energy contributes to the total energy density, to omega. When you add up ordinary matter, dark matter, and dark energy, you get a total omega very close to 1, which means space is very nearly flat. The cosmic acceleration we observe is consistent with a flat universe dominated by dark energy, and this matches beautifully with predictions from cosmic inflation. We've learned that the universe is not just expanding, but accelerating. We've discovered that an invisible energy fills all of space, pushing it apart. And we've found that the cosmos is dominated by mysterious components we don't fully understand. These discoveries show us how much we still have to learn, even as they reveal the universe's fundamental geometry and ultimate destiny. Chapter 12. Mapping the Cosmos. Now that we understand the universe is expanding and filled with mysterious dark matter and dark energy, let's talk about how all the visible matter, the galaxies and stars we can actually see, are arranged throughout space. Because when astronomers started making three-dimensional maps of the universe, plotting the positions of millions of galaxies, they discovered something absolutely stunning. The universe has a structure, a pattern, an architecture on the larger scales that reveals deep truths about cosmic history and geometry. Imagine you're looking at a city from an airplane at night. From high up, you can see the pattern of street lights forming a network of roads, highways, and neighborhoods. Individual lights blur together, but the large-scale structure stands out clearly. Mapping the universe is similar, except instead of streetlights, we're mapping galaxies. And instead of seeing them from above, we're seeing them from within, looking out in all directions. For most of human history, we couldn't make such maps because we didn't know how far away anything was. We could see galaxies in the sky, but without distance information, we couldn't determine their three-dimensional positions. It's like looking at stars in a constellation. They appear to form a pattern in the sky, but some stars might be much farther away than others, and the apparent pattern is just a projection effect. The breakthrough came when astronomers developed techniques to measure galaxy distances. Using redshift as a distance indicator works remarkably well. Remember that the farther away a galaxy is, the faster it's moving away due to cosmic expansion, and the more its light is redshifted. By measuring a galaxy's redshift, you can estimate its distance. It's not perfect because galaxies also have small random motions overlaid on cosmic expansion, but it's good enough to create meaningful maps. In the 1970s and 80s, astronomers began systematic surveys to measure the redshifts of thousands of galaxies. They'd point their telescopes at small patches of sky, collect light from every galaxy in that region, split the light into spectra, and measure how much each galaxy's light was redshifted. This painstaking work took years, but slowly a three-dimensional picture of the cosmos began to emerge. And when that picture came into focus, it revealed something extraordinary. Galaxies aren't scattered randomly through space like grains of sand on a beach. They're organized into a vast cosmic web, a network of filaments, sheets and clusters surrounding enormous empty voids. Picture soap bubbles pressed together. The soap forms thin films where bubbles meet, and these films join together in a complex three-dimensional network. The insides of the bubbles are empty. Galaxies in the universe are arranged similarly. They cluster along vast filamentary structures, the cosmic equivalent of soap bubble walls, surrounding huge void regions where very few galaxies exist. Some of these structures are almost incomprehensibly large. The largest known structures in the universe are filaments and walls of galaxies stretching for hundreds of millions of light-years. To put that in perspective, the entire Milky Way galaxy is only about 100,000 light-years across. These cosmic structures are thousands of times larger than entire galaxies. One of the most famous structures is called the Sloan Great Wall, discovered in the Sloan Digital Sky Survey. This is a huge concentration of galaxies forming a structure more than 1.3 billion light-years long. It's hard to even comprehend something so vast. Light takes over 1 billion years to travel from one end to the other. At the junctions where filaments meet, you find enormous galaxy clusters containing thousands of galaxies bound together by gravity. The nearest large cluster to us is called the Virgo cluster, containing over 1,000 galaxies located about 50 million light-years away. Our own Milky Way is part of a smaller collection called the Local Group, which contains about 50 galaxies, including Andromeda and various smaller companions. Between these structures are the voids, vast regions of space where very few galaxies exist. These voids can be over 300 million light-years across. If you were somehow located in the center of a void, you'd see very few galaxies in any direction. Space would appear almost empty, a dark cosmos with only scattered distant lights. Why does the universe have this structure? Why aren't galaxies distributed more uniformly? The answer takes us back to the very early universe and those tiny density variations imprinted in the cosmic microwave background that we discussed earlier. Remember that in the infant universe there were small regions that were slightly denser than average and other regions that were slightly less dense. These variations were tiny, only about 1 part in 100,000. But gravity amplifies density variations over time. Denser regions have slightly stronger gravity, so they pull in more matter from their surroundings. This makes them even denser, which increases their gravity even more, which pulls in still more matter. It's a runaway process. Meanwhile, less dense regions lose matter to their denser neighbours. They become even less dense, eventually evolving into the voids we see today. The process is like a cosmic game of the rich getting richer and the poor getting poorer, except the currency is matter and the mechanism is gravity. Scientists can simulate this process using powerful supercomputers. They start with initial conditions matching what we observe in the cosmic microwave background, then let gravity, dark matter, and dark energy evolve the universe forward in time using the laws of physics. These simulations involve tracking the gravitational interactions of billions of particles representing dark matter. And remarkably, these computer simulations produce a cosmic web that looks strikingly similar to what we observe with telescopes. Filaments form where dark matter streams together. Clusters form at the junctions. Voids expand where matter is underdense. The match between simulation and observation is one of the great triumphs of modern cosmology. It shows that we really do understand, at least in broad strokes, how cosmic structure formed and evolved. The simulations also reveal something important about dark matter. The cosmic web is primarily a dark matter structure. Dark matter provides the gravitational scaffolding, and ordinary matter falls into that scaffolding, accumulating in the densest regions where it can form stars and galaxies. Without dark matter, the universe wouldn't have enough gravity to form the structures we observe. Now you might wonder, what does all this structure tell us about the shape of the universe, our central question? The answer is subtle but important. On small scales, the universe is very lumpy and irregular. Our solar system is dense compared to interstellar space. Our galaxy is dense compared to intergalactic space. Galaxy clusters are dense compared to voids. But on the very largest scales, when you look at regions hundreds of millions or billions of light-years across, the universe becomes remarkably uniform. If you average over large enough volumes, every region has roughly the same density. The distribution of matter becomes homogeneous and isotropic, meaning it's the same everywhere and looks the same in all directions. This large-scale uniformity is crucial for cosmology. It means that our theories describing the universe as a whole make sense. We can talk about the universe having a shape, because on large scales it really is uniform. If the universe were wildly different in different regions, with radically different densities and properties in different places, talking about a single cosmic shape or geometry wouldn't make sense. This uniformity also supports the idea that we don't occupy a special location. The universe looks roughly the same from any galaxy's perspective. This principle, called the cosmological principle, is a foundational assumption of modern cosmology. And the large-scale structure observations confirm it's valid. The cosmic web also provides another way to measure cosmic geometry. The characteristic scale of structures, how big typical filaments and voids are, depends on the geometry of space. In a positively curved universe, structures would appear compressed. In a negatively curved universe, they'd appear stretched. In a flat universe, they appear at the scale predicted by our understanding of how gravity amplifies density variations. When scientists analyze the distribution of galaxies and compare it to predictions for different geometries, they find, once again, that the universe is flat. The scale of structures matches what's expected for flat geometry. This provides independent confirmation of what we learned from the cosmic microwave background. The cosmic web is also beautiful in its own right. When you see visualizations of the large-scale structure, the intricate lacework of galaxies threading through space, it's hard not to feel awe. This is the architecture of the universe laid bare. This is the pattern imprinted by gravity acting on quantum fluctuations from the first moments of cosmic time. And there's something poetic about the fact that we, collections of atoms assembled in this cosmic web, have developed the tools and understanding to map the web's structure. We're part of the cosmos that has become aware of itself, studying its own architecture and history. The maps of cosmic structure represent centuries of human effort, from the first crude catalogues of nebulae to modern surveys measuring millions of galaxy positions. They reveal that the universe has order and pattern on the largest scales, that it evolved from simple initial conditions following comprehensible physical laws, and that its geometry is remarkably close to flat. Chapter 13. Measuring the universe's shape. We've talked about how the universe could be positively curved like a sphere, negatively curved like a saddle, or perfectly flat. We've discussed how the density of matter and energy determines which geometry is real. But now we need to talk about how scientists actually measure the shape of space itself. How do you determine the geometry of something when you're inside it and can't step outside to look at it from an external perspective? This is one of the most remarkable achievements of modern cosmology. Scientists have found ways to measure cosmic geometry using what amounts to cosmic rulers, standard measuring sticks whose true size we know, allowing us to determine whether space curves or remains flat. It's a bit like how the ancient Greeks determined Earth was a sphere by making careful measurements from the surface, never leaving the ground. The most powerful cosmic ruler comes from sound waves in the early universe. Yes, you read that right. Sound waves. Let me explain how this works because it's absolutely fascinating. In the first few 100,000 years after the Big Bang, before atoms formed and the universe became transparent, the cosmos was filled with hot plasma. This plasma could support sound waves, pressure waves, traveling through the fluid mixture of matter and radiation. These weren't sound waves like you'd hear with your ears. They were enormous waves on cosmic scales. But they behaved according to the same physics that governs sound in air. Regions of higher density would compress and then bounce back, creating oscillations in the plasma's density. These oscillations, driven by the interplay between gravity trying to compress matter and radiation pressure trying to expand it, created a characteristic pattern. The crucial point is that we know exactly how large these sound waves should be. The size depends on fundamental physics, like the speed of sound in the early universe plasma, which we can calculate precisely. These sound waves had a specific wavelength, a characteristic size, determined by how far sound could travel in the time between the Big Bang and when atoms formed. When atoms finally did form and the universe became transparent, the sound waves froze in place. They left an imprint, a fossilized pattern in how matter was distributed. Regions where sound waves created compressions became slightly overdense. Regions where they created rarefactions became slightly underdense. And this pattern persists to the present day in how galaxies are distributed. Astronomers call this pattern baryon acoustic oscillations, or BAO for short. The word baryon just refers to ordinary matter made of protons and neutrons. The oscillations are those sound waves from the early universe, and we can detect this pattern by carefully measuring the distribution of galaxies. When you plot the distances between pairs of galaxies and look at the statistical distribution, you find an excess of galaxy pairs separated by a specific distance, about 500 million light-years. This excess represents the characteristic scale imprinted by those primordial sound waves. It's like a cosmic standard ruler embedded in the structure of the universe. And here's why this is so useful for measuring cosmic geometry. We know the true physical size of this ruler, about 500 million light-years. But the angular size, how large it appears in the sky, depends on the geometry of space. Think about how this works. Imagine you're looking at a meter stick that's 10 meters away from you. In flat space, you can calculate exactly what angular size it should have in your field of view using simple trigonometry. But in curved space, light travels along curved paths, and the same meter stick at the same distance would appear to have a different angular size. In a positively curved universe, like the surface of a sphere, light rays converge. Objects appear larger than they would in flat space, like looking through a magnifying lens. In a negatively curved universe, light rays diverge. Objects appear smaller than they would in flat space. By measuring the angular size of the baryon acoustic oscillation feature and comparing it to the known physical size, scientists can determine whether space is curved or flat. The cosmic microwave background provides an even more direct measurement. Remember those tiny temperature variations across the sky, imprinted when the universe was just 380,000 years old. Those variations also have a characteristic angular scale determined by the same primordial sound waves. Scientists can measure the sizes of hot and cold spots in the cosmic microwave background with exquisite precision. The Planck satellite measured these patterns across the entire sky with angular resolution better than 10 arc-minutes, which is about 1/3 the diameter of the full moon. When cosmologists analyze these patterns, they find peaks at specific angular scales corresponding to sound waves of different wavelengths. The position of these peaks tells you the geometry of space. If space were positively curved, the peaks would shift to larger angular scales. If space were negatively curved, they'd shift to smaller angular scales. In flat space, the peaks appear at a specific set of angular positions predicted by theory. And what do the observations show? The peaks appear exactly where they should for a flat universe. The agreement is remarkable, precise to better than 1%. When scientists fit the data to models with different curvatures and different values of omega, the best fit is consistently omega equals 1 to within less than 0.5%. Multiple independent measurements all point to the same conclusion. The baryon acoustic oscillation scale in galaxy surveys, the angular scale of temperature fluctuations in the cosmic microwave background, the relationship between distance and redshift for supernova, the ages of the oldest stars, all these different methods converge on the same answer. The universe is spatially flat to within the precision of our measurements. This flatness is actually quite remarkable when you think about it. Remember the flatness problem we discussed earlier. For the universe to be flat today, it must have been extraordinarily close to flat in the early universe. The fact that we measure omega so close to 1 is strong evidence for cosmic inflation, which predicts that inflation should drive omega extremely close to 1, regardless of what value it started with. But there's something important I need to clarify. When we say the universe is flat, we're talking about its spatial geometry, the geometry of space at a given moment in cosmic time. We're not saying space-time as a whole is flat. Remember that space-time is four-dimensional, combining 3 dimensions of space with 1 of time. The overall geometry of space-time is definitely not flat because the universe is expanding. Time and space are curved together in a specific way described by Einstein's equations. What we mean by a flat universe is that if you could somehow freeze time and measure the geometry of 3-dimensional space at that frozen instant, you'd find that space obeys the rules of Euclidean geometry. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. The ratio of a circle's circumference to its diameter is exactly pi. All the geometric relationships you learned in high school are accurate on cosmic scales. This has profound implications for the universe's extent. A flat universe can be infinite in spatial extent. There's no edge, no boundary, no place where space stops. You could travel in any direction forever and never reach an end. Of course, you can't actually do this because you're limited by the speed of light and the finite age of the universe. But in principle, space extends infinitely in all directions. However, and this is where things get interesting, a flat universe doesn't have to be infinite. There are exotic topological possibilities where space could be flat but still have finite volume. Imagine a video game where the screen wraps around. When your character exits the right edge, it reappears on the left edge. The screen itself is flat, but the space it represents loops back on itself. Mathematicians call this a torus topology. The same thing is possible in 3 dimensions. Space could be flat in the sense that local geometry obeys Euclidean rules, but the overall topology could connect distant regions. If you traveled far enough in one direction, you might eventually return to your starting point from the opposite direction, even though you never turned around, and even though space is locally flat everywhere. We'll explore these exotic topologies in more detail in a later chapter. For now, the key point is that observations tell us space is very nearly flat. The total energy density of the universe, including ordinary matter, and dark energy, adds up to almost exactly the critical density. Omega equals 1 to within our measurement precision, and this flatness emerged from the intense physics of the very early universe during the inflationary epoch. The tools scientists use to measure cosmic geometry represent an incredible synthesis of observational astronomy, theoretical physics, and mathematical analysis. From studying ancient light in the cosmic microwave background, to mapping the positions of millions of galaxies, to measuring the brightness of distant exploding stars, every piece of evidence points to the same geometric conclusion. We live in a flat universe, one that obeys the familiar rules of Euclidean geometry on the largest scales, even though it's filled with mysterious dark matter and dark energy, and even though its ultimate fate involves eternal expansion and eventual emptiness. The measurement of cosmic flatness stands as one of the great achievements of human science. We've determined the geometry of space itself, answering a question that would have seemed impossibly abstract to previous generations. And we've done it with precision and confidence, using multiple independent methods that all converge on the same answer. The universe's shape is no longer a mystery. It's a measured, confirmed aspect of cosmic reality. Chapter 14. Strange Topologies. Now, I want to take you into some truly mind-bending territory. We've established that the universe appears to be spatially flat, that space obeys the rules of Euclidean geometry on large scales. But here's something that might surprise you. A flat universe doesn't necessarily mean the universe is infinite. There are strange and beautiful ways that space could be flat locally, following all the geometric rules we've discussed, while still having finite total volume. To understand this, we need to distinguish between two different properties of space. There's geometry, which describes how distances and angles work, whether parallel lines stay parallel or converge or diverge. And there's topology, which describes the overall connectivity and structure of space, whether it loops back on itself or extends forever. Let me give you an analogy that will help make this clear. Think about a flat sheet of paper. It has flat geometry. If you draw a triangle on it, the angles add up to 180 degrees. Parallel lines stay parallel. Everything obeys Euclidean geometry. Now imagine taking that sheet of paper and taping the left edge to the right edge without twisting or crumpling the paper. You've created a cylinder. Here's the remarkable thing. The surface of that cylinder is still locally flat. If you're an ant walking on the cylinder, at any point, the geometry around you is exactly the same as it was on the flat sheet. Triangles still have angles adding to 180 degrees. Parallel lines are still parallel. The curvature is still zero, but the topology has changed. Now, if you walk in one direction long enough, you'll return to where you started, even though you never turned around. you can do something even more interesting. Take your original flat sheet and connect the left edge to the right edge and the top edge to the bottom edge. You've created what mathematicians call a two-dimensional torus, like the surface of a donut, except this donut has no curvature. It's a flat torus, which seems paradoxical when you try to visualize it in three-dimensional space. And that's because a truly flat torus can't exist embedded in three dimensions. It's an abstract topological structure that you can describe mathematically, even if you can't build a physical model of it. The same principle applies to three-dimensional space. You could have a universe where the geometry is perfectly flat, where Euclidean rules apply everywhere, but where space wraps around and connects to itself. If you travelled far enough in one direction, you'd eventually return to your starting point from what appears to be the opposite direction. This is called a three-torus, and it's just one of several possible topologies for a flat universe. Mathematicians have actually classified all the possible topologies for flat three-dimensional spaces. It turns out there are exactly 18 different possibilities, each with its own unique pattern of how space connects to itself. Some of these topologies involve simple wrapping in all three directions, like the three-torus we just discussed. Others are more exotic. In one topology, space might twist as it wraps around, like a Mobius strip, but in three dimensions. In another, space might connect back to itself in complex patterns involving reflections and rotations. Now you might be wondering, why should we care about these abstract mathematical possibilities? Don't we already know the universe appears flat, and isn't that enough? The reason these exotic topologies matter is that they're actually testable. If the universe has one of these wrapped topologies, we might be able to detect it through observations. Here's how it would work. Imagine the universe is a three-torus, and the wrapping scale is smaller than the observable universe. Light from a distant galaxy would have multiple paths to reach us. It could come directly, or it could wrap around the universe one or more times before reaching us. This means we might see the same galaxy in multiple directions in the sky, appearing as different objects because the light took different paths to reach us. It's like standing in a hall of mirrors. You see multiple images of yourself reflected from different directions, but they're all images of the same person. In a wrapped universe, we might see multiple images of the same galaxy or cluster of galaxies appearing in different parts of the sky. We could also look for repeating patterns in the cosmic microwave background. If space wraps around on scales smaller than the observable universe, the pattern of temperature fluctuations should repeat in specific ways. The exact repetition pattern would depend on which of the 18 possible topologies the universe has. Astronomers have actually searched for these signatures. They've looked for pairs of galaxy clusters that might be the same cluster seen twice. They've analyzed the cosmic microwave background for repeating patterns. So far, they haven't found any convincing evidence for cosmic topology. This tells us that if the universe wraps around, it does so on scales larger than the observable universe. The current constraints suggest that if the universe is a three-torus, each dimension must be at least as large as the observable universe, which is about 93 billion light-years across. This means the wrapping, if it exists, happens on scales we can't currently observe. The universe might be finite, but still much, much larger than the region we can see. There's something both humbling and exciting about this. We might live in a finite cosmos, but one so vast that we'll never be able to see its full extent. The observable universe, everything we can possibly see with any telescope, no matter how powerful, might represent just a tiny fraction of the total universe. Or the universe might truly be infinite, extending forever in all directions, with no wrapping or boundaries. In an infinite flat universe, there would be infinitely many galaxies, infinitely many stars, infinitely many planets. And here's where things get really strange. In an infinite universe with quantum mechanics, every possible arrangement of matter that can exist will exist somewhere, repeated infinitely many times. This means there would be infinitely many planets exactly like Earth. Infinitely many people exactly like you. Infinitely many versions of this exact moment happening elsewhere in an infinite cosmos. The idea seems absurd, but it's a logical consequence of infinite space combined with quantum mechanics, which says that all possible quantum states have some probability of occurring. Most cosmologists suspect the universe is indeed infinite, rather than having wrapped topology, simply because we haven't detected any evidence for wrapping, and the inflationary theory that explains cosmic flatness also tends to produce infinite universes. But we can't be certain. The possibility of exotic topology remains open. There are also more speculative ideas about cosmic topology. Some theories suggest that different regions of space might have different topologies, with topological transitions at certain boundaries. Others propose that space might have a fractal structure, with similar patterns repeating at different scales. These ideas are much more speculative and harder to test, but they remind us that the actual structure of space might be stranger than anything we've imagined. What I find most fascinating about cosmic topology is that it shows how observations can constrain even extremely abstract mathematical possibilities. The question of whether space wraps around isn't just philosophy or mathematics. It's something we can actually investigate through careful observation and measurement. We can look at the patterns in the cosmic microwave background, catalogue the positions of galaxies, and use this data to test whether space has exotic connectivity. The fact that we haven't detected cosmic topology tells us something important. Either the universe is infinite, or if it's finite, it's vastly larger than the region we can observe. Either possibility is profound. An infinite universe challenges our intuitions and raises deep questions about probability, identity, and the nature of existence. A finite but unimaginably vast universe reminds us of the limits of human knowledge and the humility appropriate when contemplating cosmic questions. The topology of space represents one of the deepest questions we can ask about reality's structure. Is space infinite or finite? Does it loop back on itself or extend forever? These questions touch on fundamental issues in mathematics, physics, and philosophy, and remarkably, we've made real progress in answering them through observation and theory, even if definitive answers remain elusive. The search for cosmic topology continues. Future surveys will map the universe in even greater detail, looking for any hint of repeating patterns or wrapped structure. Future analysis of the cosmic microwave background will constrain topology on ever larger scales. And theoretical work continues to explore what different topologies would imply for cosmic evolution and structure formation. For now, we know that space is very nearly flat in its geometry. Whether it's also infinite in its extent remains an open question, one of the great unsolved mysteries about the universe's true shape. Chapter 15. The multiverse possibility. We've been talking about the universe singular as if there's only one cosmos to consider. But what if that assumption is wrong? What if our universe, vast as it is, represents just one bubble in an infinitely larger reality? What if there are countless other universes beyond our cosmic horizon, each with potentially different laws of physics, different constants of nature, maybe even different numbers of dimensions? This is the idea of the multiverse, and it emerges naturally from some of our best theories about cosmic origins. Let me take you back to cosmic inflation, that brief period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. Remember that inflation solved several major puzzles about the universe. It explained why space appears so flat. It explained why the universe looks uniform in all directions, even though distant regions apparently never had time to exchange information. And it explained where the tiny density variations came from that eventually grew into galaxies. But here's something remarkable about inflation. If it happened once, it's probably happening all the time in different regions of a larger reality. Let me explain why physicists think this. Inflation is driven by a quantum field, a kind of energy that fills space. Think of it like a ball sitting at the top of a hill. The ball has potential energy because of its position, and if it starts rolling down the hill, that potential energy gets converted into motion. In the inflationary scenario, space is filled with this quantum field sitting in a high-energy state, like a ball perched on a hilltop. When the field rolls down to a lower energy state, the potential energy gets released, and that release drives the rapid expansion of space. Eventually, the field reaches the bottom of its energy hill, inflation ends, and the released energy converts into matter and radiation, creating the hot Big Bang we observe. But quantum mechanics tells us that fields don't behave like smooth, continuous things. They're subject to quantum fluctuations, random jitters caused by the inherent uncertainty in quantum physics. These fluctuations are happening everywhere, all the time. In most regions, the quantum field rolls smoothly down its energy hill and inflation ends. But in some regions, quantum fluctuations might kick the field back up the hill, causing inflation to continue in those regions even after it's ended elsewhere. This creates a remarkable picture. Inflation ends in some patches of space, creating regions like our observable universe where matter and radiation exist and galaxies can form. But in the regions between these patches, inflation continues and space keeps expanding exponentially. Then inflation ends in some of those regions too, creating more bubble universes. But it continues in other regions which then spawn more bubbles, and so on forever. This is called eternal inflation, and it's a natural consequence of combining inflation with quantum mechanics. Once inflation starts anywhere, it never completely stops everywhere. It keeps creating new bubble universes eternally into the future. Each bubble is an entire universe unto itself, potentially infinite in its own right, but surrounded by an eternally inflating space that's creating more and more bubbles. Now, here's where things get truly strange. The properties of each bubble universe, the laws of physics that operate within it, might be different from bubble to bubble. To understand why, we need to talk about something called the vacuum state, or the ground state, of quantum fields. In particle physics, what we call empty space isn't truly empty. It's filled with quantum fields in their lowest energy states. And it turns out there might be many different possible ground states for these fields, potentially an enormous number of them. Some theories, particularly string theory, suggest there could be something like 10 to the power of 500 different possible vacuum states. Each vacuum state would correspond to a universe with different properties. The masses of fundamental particles might be different. The strength of forces like electromagnetism or gravity might vary. There might be different numbers of particle types. The cosmological constant, which we observe as dark energy, would almost certainly be different. Some universes might have more dimensions of space. Others might have fewer. When a region of eternally inflating space transitions into a bubble universe, it randomly settles into one of these many possible vacuum states. This means each bubble universe could have radically different physics from every other bubble. Most of these universes would be utterly inhospitable to life. In some, matter might not be stable. In others, stars couldn't form. In still others, atoms couldn't exist. But in a tiny fraction of bubbles, the physics happens to be compatible with complexity, chemistry, and eventually life. This brings us to something called the anthropic principle. This principle observes that we shouldn't be surprised to find ourselves in a universe with properties compatible with our existence, because we couldn't exist in universes with different properties. It's a selection effect. Out of countless bubble universes with different physics, we necessarily inhabit one of the rare ones where observers like us can arise. This anthropic reasoning potentially explains some puzzling features of our universe. For instance, why is the cosmological constant so incredibly small compared to what quantum field theory predicts, yet still non-zero? In most universes, a large cosmological constant would cause space to expand so rapidly that galaxies never form. In universes with zero cosmological constant, conditions might also be unsuitable for life for other reasons. We find ourselves in a universe with a small but non-zero value simply because that's one of the narrow ranges where life is possible. Similarly, why are the fundamental constants of nature so finely tuned to allow for chemistry, stars and planets? If the strength of the electromagnetic force was slightly different, atoms wouldn't be stable. If the strong nuclear force was slightly different, atomic nuclei couldn't form. If gravity were much stronger, stars would burn out too quickly for life to evolve. If it were much weaker, stars might not ignite at all. In a multiverse with different physics in different regions, these apparent fine-tunings become less mysterious. We observe fine-tuned values because we exist in one of the rare universes where those values permit observers. Now, I need to be very clear about something. The multiverse idea is highly controversial among physicists. Some embrace it enthusiastically as a natural consequence of our best theories. Others reject it as unscientific speculation. The controversy centers on a fundamental question about what makes something scientific. Science traditionally works by making predictions that can be tested through observation and experiment. You propose a hypothesis, derive what it predicts, then check whether observations match those predictions. If they do, the hypothesis gains support. If they don't, the hypothesis is ruled out. This process requires that the hypothesis make definite, testable predictions. The challenge with the multiverse is that by definition, other universes are beyond our cosmic horizon. We can never observe them directly. Light from other bubble universes can never reach us because the eternally inflating space between bubbles expands far faster than light can traverse it. So, how can we possibly test whether the multiverse exists? Defenders of multiverse theories argue that we can test them indirectly. Eternal inflation makes predictions about properties of our universe that we can verify. If those predictions match observations while competing theories fail, that's evidence for eternal inflation, and the multiverse comes along as a consequence. The theory is tested through its successful predictions about the observable universe, even if we can't directly observe the unobservable parts. Critics counter that this isn't good enough. If a theory predicts the existence of things that are in principle impossible to observe, those predictions aren't really scientific. Some critics argue that anthropic reasoning is particularly troublesome because it can explain almost anything. Why does the universe have any particular property? Because if it didn't, we wouldn't be here to observe it. This kind of reasoning, critics say, isn't truly explanatory. There's also a deeper problem with multiverse theories related to probability. In an infinite multiverse where everything possible happens infinitely many times, how do you calculate the probability of observing any particular thing? This is called the measure problem, and it remains unsolved. Different ways of counting lead to different probability predictions, and we have no principal way to decide which counting method is correct. Despite these controversies, many physicists take the multiverse seriously because it emerges naturally from theories that successfully explain other phenomena. Cosmic inflation explains the flatness, uniformity, and density variations of our observable universe remarkably well. Eternal inflation is a straightforward consequence of combining inflation with quantum mechanics. The multiverse follows naturally from eternal inflation. So even though we can't observe other universes directly, the theoretical framework that predicts them has proven successful in other ways. String theory, one of the leading candidates for a fundamental theory unifying quantum mechanics and gravity, also points toward a multiverse through what's called the string theory landscape. String theory requires extra dimensions of space beyond the three we experience. The geometry of these extra dimensions, how they're curled up and connected, determines the physics of the resulting four-dimensional universe. And there appear to be an enormous number of possible geometries, each corresponding to a different vacuum state with different physics. If string theory is correct, and if eternal inflation is real, then the landscape of possibilities becomes actual, with different regions of the eternally inflating space settling into different vacua and creating bubble universes with different physics drawn from the string theory landscape. What does all this mean for the question of cosmic shape? It means the universe we can observe, with its flat geometry and specific physical properties, might be just one small patch in an inconceivably vaster reality. Our observable universe has a shape, flat spatial geometry within an expanding space-time. But the universe in the largest sense might have no single shape at all. Different bubble universes might have different geometries. Some might be positively curved, others negatively curved, others flat like ours. The multiverse as a whole might not have a well-defined shape in any conventional sense. This is simultaneously humbling and awe-inspiring. Humbling because it suggests that even our vast observable universe, with its hundreds of billions of galaxies stretching across billions of light years, might be infinitesimally small compared to the totality of existence. Awe-inspiring because it reveals that reality might be far richer, far more diverse, far stranger than we ever imagined. The multiverse idea also raises profound philosophical questions. If there are infinitely many universes with every possible set of physical laws, does our universe become less special, less meaningful? Or does the fact that we exist to contemplate these questions give our existence a different kind of significance? If every possible universe exists somewhere, what determines which one we find ourselves in? These questions blur the boundaries between physics, philosophy, and even theology. For now, the multiverse remains a theoretical possibility rather than an established fact. We have good theories that predict it, but we lack definitive observational confirmation. Future observations might provide indirect evidence. For instance, if we detected signs of collisions between our bubble universe and neighboring bubbles in the pattern of the cosmic microwave background, that would strongly support the multiverse hypothesis. So far, searches for such signatures have come up empty, but the search continues. Whether the multiverse is real or not, contemplating it stretches our minds and challenges our assumptions about reality. It reminds us that the universe we observe, remarkable as it is, might be just one thread in a much larger cosmic tapestry. And it shows how scientific theories, when pushed to their logical conclusions, can lead to ideas that seem more like science fiction than sober physics, yet emerge naturally from our most successful mathematical descriptions of nature. Chapter 16. Inside a Black Hole. Now I want to take you to the most extreme environment in the universe, a place where space-time curvature becomes so intense that our normal intuitions completely break down. I want to take you inside a black hole. Black holes represent the ultimate warping of space and time, and understanding their geometry helps us grasp what extreme curvature means and how it relates to the overall shape of the cosmos. Let me start by explaining what a black hole actually is. Despite their exotic reputation, black holes are remarkably simple objects from a theoretical perspective. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon, and it's the point of no return. Black holes form when massive stars exhaust their nuclear fuel and collapse. During its life, a star is supported against gravitational collapse by the outward pressure from nuclear fusion in its core. Hydrogen fuses into helium, releasing energy that creates pressure pushing outward. This pressure balances gravity, pulling inward. But when the fuel runs out, there's nothing left to support the star against its own gravity. For stars below a certain mass, about 20 to 30 times the mass of our Sun, the collapse can be halted by other quantum mechanical effects. The star might become a white dwarf or a neutron star, incredibly dense but not infinitely collapsed. But for stars above that mass threshold, nothing can stop the collapse. Gravity overwhelms every force of resistance, and the star's core collapses down to infinite density, creating what physicists call a singularity. The singularity itself is hidden behind the event horizon. The event horizon forms at a specific radius from the singularity called the Schwarzschild radius, named after the physicist who first calculated it. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. For a black hole with 1,000,000 times the Sun's mass, like those found at the centers of galaxies, the Schwarzschild radius is about 3 million kilometers. Here's the crucial thing to understand about the event horizon. It's not a physical surface. It's not made of anything. It's simply a boundary in space-time, a point beyond which the escape velocity exceeds the speed of light. Before you cross it, you could still escape by firing your rocket engines. After you cross it, you're doomed to fall toward the singularity no matter what you do, because doing so would require moving faster than light, which is impossible. The geometry of space-time near a black hole is profoundly warped. Far from the black hole, space is nearly flat, with only small gravitational effects. As you approach the event horizon, the curvature of space-time becomes increasingly severe. Light no longer travels in straight lines. Time passes at different rates depending on how close you are to the horizon. If you watched a clock falling toward a black hole from a safe distance, you'd see it tick slower and slower as it approached the horizon, never quite reaching it from your perspective because time appears to stop at the horizon for outside observers. But from the perspective of someone falling into the black hole, something very different happens. You would cross the event horizon in finite time according to your own clock. You wouldn't notice anything particularly special about the moment of crossing for a large black hole. There's no sign, no barrier, no sudden change. You'd simply pass through and find yourself unable to escape. And here's where the geometry becomes truly bizarre. Inside the event horizon, the roles of space and time get mixed up in a strange way. The direction toward the singularity, which was a direction in space before you cross the horizon, becomes a direction in time after you cross. Just as you cannot avoid moving forward in time in ordinary space, you cannot avoid moving toward the singularity once you're inside the horizon. Reaching the singularity becomes as inevitable as reaching the next second. You can delay it briefly by firing rockets, just as you might try to hold your breath to delay the next moment. But ultimately, you must arrive at the singularity just as you must arrive at future moments in time. The geometry of space-time inside a black hole makes this fate absolutely unavoidable. What happens as you approach the singularity? For smaller black holes, you'd be torn apart by tidal forces long before reaching it. Tidal forces arise because gravity is stronger closer to the black hole. Your feet, if they're closer to the singularity than your head, experience stronger gravity and get pulled harder. This difference in gravitational pull stretches you like taffy in a process scientists call spaghettification. For supermassive black holes, the ones millions or billions of times the mass of our Sun found at galaxy centers, the situation is different. The event horizon is so far from the singularity that tidal forces at the horizon are relatively gentle. You could cross the event horizon of a supermassive black hole and survive for a while, falling through a region of space where nothing seems particularly unusual except that you can't turn around and escape. But eventually, as you approach the singularity, tidal forces would become irresistible and you'd be torn apart. And at the singularity itself, space-time curvature becomes infinite. Our equations break down completely. We don't know what happens at the singularity because our physical theories can't describe conditions of infinite curvature and density. This is where quantum gravity, a theory we don't yet have, would be essential to understand what's really going on. Black holes raise a profound puzzle called the information paradox. According to quantum mechanics, information cannot be destroyed. If you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any other time, forward or backward. Information is preserved. But black holes seem to destroy information. If you throw a book into a black hole, all the information in that book, every arrangement of letters, seems to vanish forever once it crosses the event horizon and reaches the singularity. Stephen Hawking complicated this puzzle in the 1970s when he discovered that black holes aren't entirely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate, eventually disappearing completely over astronomical timescales. A black hole with the Sun's mass would take about 10 to the power of 67 years to evaporate through Hawking radiation. But eventually it would vanish. So here's the paradox. Information falls into a black hole. The black hole eventually evaporates. Where did the information go? Did it vanish, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation? And if so, how? This problem has occupied theoretical physicists for decades. The current leading idea is that information is indeed preserved, somehow encoded in subtle correlations in the Hawking radiation. but exactly how this works remains unclear. Black holes also connect to larger questions about cosmic geometry in interesting ways. Some theoretical solutions to Einstein's equations involve black holes connected to white holes through structures called wormholes or Einstein-Rosen bridges. A white hole would be the time reverse of a black hole, a region that nothing can enter, but from which things can escape. In principle, you might fall into a black hole and emerge from a white hole somewhere else, either in a different part of our universe or in a completely different universe. However, these wormhole solutions are extremely unstable. They would collapse too quickly for anything to pass through. To keep a wormhole open would require exotic matter with negative energy density, something we've never observed and may not exist. So, while wormholes are mathematically possible solutions to Einstein's equations, they're probably not physically real, at least not in any form that could be traversed. Still, the existence of these solutions in general relativity shows how rich and strange space-time geometry can be. The fabric of space and time permits structures far more exotic than the gently curved space we observe on cosmic scales. Black holes, with their event horizons and singularities, represent the most extreme curvature that exists in our universe. They're natural laboratories for testing our understanding of gravity in extreme conditions. Studying black holes also helps us understand what it means for space to be curved. When we say the universe is flat on large scales, we mean that averaged over enormous regions, space-time curvature approaches zero. But locally, near massive objects, curvature can be severe. Black holes represent the limit of this local curvature, the most warped regions of space-time that can exist. The centers of most galaxies, including our own Milky Way, harbor supermassive black holes. Our galaxy's central black hole has about 4 million times the Sun's mass. It's surrounded by stars orbiting at tremendous speeds, and we can track these orbits to map out the extreme space-time curvature in that region. These observations provide some of our best tests of general relativity in strong field conditions. In recent years, we've even managed to directly image black holes. The Event Horizon Telescope, a global network of radio telescopes working together, has captured images showing the shadow of the supermassive black hole at the center of the galaxy M87 and our own galactic center. These images show the distorted light from hot gas swirling around the event horizon, bent into a ring by the extreme curvature of space-time. It's a direct visual confirmation of these exotic objects that were once purely theoretical. Black holes remind us that space-time is dynamic and can be sculpted into almost unimaginably curved configurations. They represent the universe at its most extreme, places where our physical theories are pushed to their limits and beyond. Understanding black hole geometry deepens our appreciation for what curvature means and how dramatically different it can be from the gentle, nearly flat geometry we observe on cosmic scales. The universe's overall shape is flat or very nearly so, but that flatness is an average, a large-scale property. Zoom in and you find a cosmos rich with structure, from the gentle curvature around stars and planets to the extreme warping around black holes. This hierarchy of curvature, from cosmic flatness to black hole extremes, characterizes the geometry of the universe we inhabit. Chapter 17. Quantum Foam and the Smallest Scales. We've been exploring the universe at the largest scales, from the cosmic microwave background to the distribution of galaxies across billions of light years. We've measured the flatness of space and contemplated the possibility of infinite extent. But now I want to take you in the opposite direction. I want to shrink down to the smallest possible scales, to distances so tiny that they make atoms look like galaxies by comparison. Because at these infinitesimal scales, something remarkable happens. Space itself might stop being smooth and continuous. It might become grainy, turbulent, perhaps even chaotic. To understand what happens at the smallest scales, we need to talk about something called the Planck length. This is a fundamental scale in physics, a distance so small that our normal concepts of space and time begin to break down. The Planck length is approximately 1.6 times 10 to the negative 35 meters. Let me put that in perspective for you. An atom is about 10 to the negative 10 meters across. The Planck length is about 100 million trillion times smaller than an atom. If an atom were the size of the entire observable universe, the Planck length would be about the size of a tree. Why is this particular scale so important? The Planck length emerges naturally when you combine three fundamental constants of nature. There's the speed of light from Einstein's relativity, which sets a universal speed limit. There's Planck's constant from quantum mechanics, which describes how quantum effects become important. And there's Newton's gravitational constant, which determines the strength of gravity. When you mathematically combine these three constants, you get the Planck length. What makes the Planck length special is that it's the scale where quantum mechanics and gravity both become equally important. At larger scales, you can usually ignore one or the other. When you're studying atoms, quantum mechanics matters, but gravity is negligible. When you're studying planets and stars, gravity matters, but quantum mechanics is usually unimportant. But at the Planck scale, both quantum mechanics and gravity are crucial, and we need a theory that unifies them to describe what's happening. The problem is, we don't have such a theory yet. General relativity describes gravity beautifully, but doesn't incorporate quantum mechanics. Quantum field theory describes particles and forces wonderfully, but treats space-time as a fixed background rather than something dynamic that gravity can curve. These two pillars of modern physics are fundamentally incompatible in their current forms. At the Planck scale, this incompatibility becomes critical. We simply don't know for certain what space and time are like at these distances. But physicists have developed some compelling ideas based on combining what we do know from quantum mechanics and relativity. One of the most striking predictions is that at the Planck scale, space-time itself becomes subject to quantum fluctuations. Let me explain what this means. In quantum mechanics, everything is subject to uncertainty. The position and momentum of particles fluctuate. Energy fluctuates. Even in completely empty space, quantum fields are constantly bubbling with activity. According to quantum field theory, what we call the vacuum, empty space with nothing in it, is actually seething with quantum activity. Virtual particle and antiparticle pairs constantly pop into existence, exist for a brief moment, then annihilate each other and disappear. These virtual particles aren't directly observable, but they have real effects. They slightly change the properties of atoms. They create measurable forces between metal plates in vacuum. The vacuum is anything but empty at the quantum level. Now imagine applying this same quantum uncertainty to space-time itself. Just as electromagnetic fields fluctuate and create virtual particles, the geometry of space-time might fluctuate at the Planck scale. The smooth fabric of space that we experience at human scales might become turbulent and chaotic when you zoom in far enough. Physicists call this quantum foam or space-time foam. What would quantum foam look like if you could somehow observe it? Picture the surface of the ocean. From an airplane flying high above, the ocean looks smooth and blue. But as you descend, you start to see waves. Closer still, you see ripples and foam. At the smallest scales, you find droplets and spray, a chaotic froth where the distinction between water and air becomes blurry. Space-time might be similar. Smooth at large scales, but increasingly turbulent as you zoom in, until at the Planck scale it becomes a chaotic foam where the usual notions of distance and time break down. In this quantum foam, the geometry of space might be constantly fluctuating. Tiny wormholes might pop in and out of existence. Virtual black holes might form and evaporate in unimaginably brief instants. The topology of space might be constantly changing at these scales. Space might not even have a definite dimensionality. It might fluctuate between different numbers of dimensions from moment to moment. These ideas sound like pure fantasy, but they emerge from serious attempts to understand what happens when you combine quantum mechanics with general relativity. Different approaches to quantum gravity make different specific predictions, but most agree that something strange happens to space-time at the Planck scale. One approach to quantum gravity is called loop quantum gravity. In this theory, space itself is not continuous, but is made up of discrete units, tiny loops of space-time woven together in a network. Think of it like fabric. From a distance, fabric looks smooth and continuous. But zoom in with a microscope and you see it's actually woven from individual threads. Loop quantum gravity suggests space is similar, with the Planck length representing the size of the fundamental threads. In loop quantum gravity, area and volume come in discrete chunks, quantum units that cannot be subdivided further. The geometry of space is built from these fundamental units connected in a network called a spin network. As this network evolves over time, it creates what's called a spin foam, a four-dimensional structure that represents the quantum geometry of space-time. This granular structure of space might have observable consequences. Light traveling through quantum space-time might interact slightly with this grainy structure. Different wavelengths of light might travel at slightly different speeds if space is fundamentally discrete rather than continuous. Astronomers have looked for such effects in gamma rays from distant cosmic explosions, but so far they haven't detected any deviation from smooth space-time. This either means the effects are too small to measure, or that space is smoother than loop quantum gravity predicts. Another approach to quantum gravity is string theory. In string theory, the fundamental constituents of reality aren't point particles, but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. An electron is one vibration pattern. A quark is another. A photon is yet another. Even gravity emerges from a particular vibration pattern called the graviton. String theory is elegant and mathematically rich, but it has a surprising requirement. It only works consistently if space-time has more than the 4 dimensions we experience. The most common version requires 10 total dimensions, 9 of space and 1 of time. Other versions require 11 dimensions. Where are these extra dimensions? String theory says they're curled up into tiny shapes, far smaller than atoms, so small that we can't detect them. The geometry of these extra dimensions, how they're curved and connected, determines the properties of physics in the 4 large dimensions we experience. Different geometries for the extra dimensions correspond to different possible universes with different particles and forces. This landscape of possibilities connects to the multiverse ideas we discussed earlier. In eternal inflation with string theory, different bubble universes might have their extra dimensions curled up in different ways, leading to different physics in each bubble. The shapes that these extra dimensions can take are called Calabi-Yau manifolds, named after the mathematicians who studied them. These are complex geometric structures that satisfy particular mathematical requirements to be consistent with string theory. They're beautiful from a mathematical perspective, with intricate symmetries and topology. But they're impossible to visualize directly because they exist in 6 dimensions rather than the 3 we can picture. String theory also predicts that at very high energies or very small distances, new dimensions might open up. What appears as a point particle in our 4-dimensional space-time might actually be a string vibrating in 10 dimensions, with 6 of those dimensions normally invisible because they're curled up so small. At the Planck scale, these extra dimensions become important, and the full 10-dimensional structure of space-time reveals itself. Both loop quantum gravity and string theory suggest that the concept of space-time as we know it breaks down at the Planck scale. Space and time might emerge from something more fundamental, something that doesn't have a simple geometric description. Just as temperature emerges from the average motion of many molecules and doesn't apply to individual atoms, space-time might emerge from some deeper quantum substrate and lose meaning when you probe too finely. Some physicists are exploring even more radical ideas. What if space and time are not fundamental at all, but are emergent properties of something else entirely? What if, at the deepest level, reality is described by information or quantum entanglement, and geometry arises from the patterns of how information is organized? There's a fascinating proposal called the holographic principle that suggests reality might work like a hologram. In a hologram, a 3-dimensional image is encoded on a 2-dimensional surface. The holographic principle proposes that everything happening in a volume of space might actually be encoded on the boundary of that volume, like a cosmic hologram. This weird idea emerged from studying black holes, but some physicists think it might apply to the universe as a whole. All these ideas about quantum space-time remain speculative because we can't directly probe the Planck scale with experiments. The energies required would be far beyond anything we can achieve with particle accelerators. To directly test physics at the Planck scale would require building an accelerator the size of a galaxy. That's not going to happen. But we might find indirect evidence. Subtle effects from quantum gravity might leave imprints in the cosmic microwave background. The very early universe, during the first moments after the Big Bang, involved Planck-scale physics, and echoes of that might persist in the pattern of temperature fluctuations we observe today. Physicists are carefully analyzing the data for any anomalies that might point to quantum gravity effects. Understanding the smallest scales of space-time connects back to our quest to understand cosmic shape in a subtle but important way. The large-scale geometry of the universe, its flatness or curvature, emerges from the behavior of space-time across vast distances. But that geometry ultimately arises from the fundamental nature of space-time itself, from how space and time work at the deepest levels. If space-time is fundamentally grainy or made of discrete units, that might place constraints on what large-scale geometries are possible. If extra dimensions exist, the shape of those dimensions determines the physics we observe in our four-dimensional world, which in turn affects cosmic evolution and structure. The connection between the smallest and largest scales is one of the beautiful symmetries in physics. We started this journey asking about the shape of the universe. We've learned that on the largest observable scales, space is remarkably flat. But we've also discovered that zoom in far enough, and space might not be the smooth, continuous fabric we imagine. It might be quantum foam, or discrete loops, or strings vibrating in extra dimensions, or something even stranger that we haven't imagined yet. The universe has a shape at every scale. At human scales, space is nearly flat, with gentle curvature from nearby masses. At the scale of black holes, curvature becomes extreme. At cosmic scales, space flattens out again on average. And at the Planck scale, the very concept of shape might dissolve into quantum uncertainty. This hierarchy of geometry, from quantum foam to cosmic flatness, represents the full geometric character of the reality we inhabit. Chapter 18. Time's shape. So far, we've focused primarily on the shape of space, asking whether it's curved or flat, finite or infinite. But there's another dimension to consider, arguably the most mysterious dimension of all. What about time? Does time have a shape? Did it have a beginning, and will it have an end? Is it linear, like a straight road, circular, like a racetrack, or something more exotic? These questions about the geometry of time are just as profound as questions about the geometry of space, and they're intimately connected to our understanding of cosmic shape. In our everyday experience, time seems fundamentally different from space. You can move freely in any direction through space. You can go left or right, forward or backward, up or down. But time seems to have a direction. We move from past to future, never the reverse. You remember yesterday, but not tomorrow. Eggs break, but don't spontaneously reassemble. We age, but never get younger. Time has an arrow, a directionality that space lacks. Einstein's theory of relativity revealed something startling about time. It's not separate from space. Time and space are woven together into a four-dimensional fabric called space-time. Events don't happen at a location in space and a moment in time separately. They happen at points in space-time, four-dimensional coordinates combining where and when. And just as space can be curved by matter and energy, so can time. In fact, you can't curve one without affecting the other. This leads to a perspective that physicists call the block universe. According to relativity, past, present and future all exist equally. They're all real, all part of the four-dimensional space-time structure. The flow of time that we experience, the feeling that the present moment is somehow special and that the future hasn't happened yet, might be an illusion of consciousness rather than a fundamental feature of reality. Imagine space-time as a four-dimensional block, like a loaf of bread. Each slice of bread represents space at a particular moment in time. Your entire life, from birth to death, exists somewhere in this loaf. Your past self, reading this sentence, exists at one location in the block. Your future self, finishing this documentary, exists at another location. Both are equally real in the block universe picture. They're just at different temporal coordinates. This perspective is strange and counterintuitive. It suggests that in some sense everything that will ever happen has already happened, existing timelessly in the four-dimensional structure of space-time. The flow of time, the sense that we're moving from past to future, would then be something about how we experience and process the world, rather than something fundamental about time itself. But if past, present and future all exist equally, why do we experience time as flowing? Why does time have an arrow pointing from past to future? This is one of the deepest puzzles in physics. The fundamental laws of physics, both quantum mechanics and general relativity, are time-symmetric. They work equally well whether time runs forward or backward. Yet our everyday experience is profoundly time-asymmetric. The answer seems to involve something called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics says that in any closed system, entropy always increases over time. Order tends to become disorder. Hot things cool down. Differences tend to even out. And this increase in entropy gives time its direction. Think about a video of an egg falling and breaking on the floor. You immediately know whether the video is playing forward or backward. An intact egg breaking into scattered shell fragments and spreading yolk is normal. But if you see scattered fragments assembling into an intact egg rising from the floor, you know the video is running backward. The direction of increasing entropy, from order to disorder, defines the arrow of time. But this raises a question. If entropy always increases, the early universe must have started in a state of very low entropy, very high order. And indeed it did. The early universe was remarkably smooth and uniform, as we can see from the cosmic microwave background. It was in a very special, low entropy state. As the universe evolved, gravity caused matter to clump, stars formed, planets formed, and complexity arose. This might seem like increasing order, but actually the total entropy of the universe increased because stars generate enormous entropy through nuclear fusion and radiation. The arrow of time, the fact that we experience time flowing from past to future, appears to be a consequence of the universe starting in a special low entropy state at the Big Bang. But why did it start that way? This is one of the deepest unsolved problems in cosmology. Some physicists think the answer involves quantum gravity and the conditions at the very beginning. Others invoke the multiverse, suggesting that our universe with its low entropy start is one of many, and we inhabit one where the conditions allow for time's arrow, because only such universes can support observers. Now let's talk about whether time had a beginning. According to the standard Big Bang model, time began at the Big Bang itself. Before the Big Bang, there was no before. Time itself came into existence along with space and energy and matter. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary where the coordinate system breaks down. This idea of time having a beginning is supported by observations of cosmic expansion. If we run the expansion backward, we reach a singularity, a point where all of space-time and matter were compressed to infinite density about 13.8 billion years ago. At that singularity, our equations break down. Time as we know it cannot be extended further into the past. However, some cosmologists have proposed models where time extends before the Big Bang in various ways. In some cyclic models, the universe undergoes endless cycles of expansion and contraction. Each cycle ends in a big crunch where the universe collapses and a new cycle begins with a new Big Bang. In these models, time has no beginning and no end. It's circular or spiral, endlessly repeating. Other models suggest that our Big Bang was a quantum tunneling event from a previous state that might have its own notion of time. Or perhaps our universe budded off from an eternally existing parent universe. In these scenarios, time didn't begin with our Big Bang, though the time before our Big Bang might be qualitatively different from time after it. All these ideas are speculative because we can't observe what happened before the Big Bang, if that concept even makes sense. The cosmic microwave background represents the earliest light we can see, from about 380,000 years after the Big Bang. Anything earlier is hidden behind an opaque wall of hot plasma. To peer earlier would require detecting gravitational waves or other signals from the very early universe, and we're still developing the technology to do that. What about the future? Will time go on forever, or will it end? The answer depends on the ultimate fate of the universe, which in turn depends on dark energy. Based on current observations, dark energy appears to be a cosmological constant, maintaining a steady density as space expands. If that's correct, the universe will expand forever, with time stretching infinitely into the future. As the universe expands and ages, it will become increasingly cold and empty. Stars will burn out. Galaxies will evaporate. Black holes will form and then slowly evaporate through Hawking radiation. After an unimaginably long time, perhaps 10 to the power of 100 years, even the most massive black holes will disappear. The universe will approach a state of maximum entropy called heat death, a cold, dark, nearly empty expanse where nothing interesting can happen anymore. But time itself would continue. There would still be a future, even if it's a monotonous future approaching perfect uniformity. In this scenario, time has a beginning at the Big Bang, but no end. It's like a half-infinite line, starting at a point and extending forever in one direction. Some more exotic fates are possible if dark energy behaves differently than we think. If dark energy strengthens over time, it could eventually become so powerful that it tears apart galaxies, then solar systems, then planets, then atoms themselves in what's called the Big Rip. This would represent a kind of end to the universe, where even the fabric of space-time might be destroyed. Whether time itself would end in a Big Rip or continue in some altered form is unclear. Alternatively, if dark energy is not constant but changes over time, the universe might eventually stop expanding and recollapse in a big crunch. This would bring us back to cyclic models where time might continue through a bounce into a new, expanding phase. There's also the question of whether time is truly continuous, or might be made of discrete moments. Quantum units of time, just as space might be made of discrete units at the Planck scale. The Planck time, about 5 × 10⁻⁻44 seconds, is the shortest interval of time that has meaning in conventional physics. Below this scale, quantum fluctuations of space-time become so large that the usual notion of time breaks down. Some theories of quantum gravity suggest that time, like space, might be granular at the Planck scale. Reality might advance in discrete ticks like frames in a movie rather than flowing smoothly. If true, this would have profound implications for the nature of causality and the structure of physical law at the deepest levels. The relationship between time and the shape of the universe is intimate. The expansion of space over time defines a particular geometry for space-time as a whole. In the standard cosmology, space-time has the geometry of a flat spatial section that expands over time. You can visualize this as a stack of flat three-dimensional spaces, one for each moment in time, with each successive space slightly larger than the previous one, representing cosmic expansion. Mathematicians describe different possible space-time geometries by their symmetries and causal structure. Our universe appears to have what's called a Friedmann-Lemaitre-Robertson-Walker geometry, which is spatially homogeneous and isotropic, meaning it looks the same at every location and in every direction. This geometry is consistent with the cosmological principle and matches observations of cosmic uniformity on large scales. The fact that time has a direction, an arrow pointing from low entropy to high entropy, from a special initial state toward ever greater randomness, is connected to the fact that the universe has a history. If time were circular, repeating endlessly, the concept of increasing entropy wouldn't work the same way. the linear character of time, beginning at the Big Bang and progressing toward an increasingly disordered future, is essential to the universe being comprehensible and having the kind of structure that allows for complexity and life. Time remains in many ways more mysterious than space. We understand the geometry of space well enough to measure whether it's curved or flat. We've mapped the distribution of matter across billions of light years. But time, experienced so intimately, yet understood so incompletely, continues to pose fundamental puzzles. Why does it flow? Why does it have a direction? Did it truly begin, and will it truly end, or are these questions based on limited perspectives? The shape of time, its geometry and topology, remains one of the great frontiers of physics and cosmology. Chapter 19. How we know what we know. I want to pause now and step back from the grand cosmic questions we've been exploring. I want to talk about something equally important. How do we actually know any of this? How can human beings, tiny creatures living on a small planet, orbiting an ordinary star in one galaxy among hundreds of billions, claim to understand the shape and structure of the entire universe? This is a remarkable achievement that deserves careful examination, because the methods we use reveal something profound about the nature of science itself. The challenge of cosmology is unique among scientific disciplines. In most sciences, you can perform experiments. If you want to understand how plants grow, you can plant seeds under different conditions and observe what happens. If you want to understand chemical reactions, you can mix substances in a laboratory and measure the results. You can control variables, repeat experiments, and test hypotheses directly. But you cannot experiment on the universe. There is only one cosmos, and we're stuck inside it. We can't create a second universe with different properties to see what happens. We can't rewind cosmic history and change the initial conditions. We can only observe, only gather information from the light and other signals that reach us from distant space and ancient times. Cosmology is fundamentally an observational science rather than an experimental one. So how do we learn about the universe? We rely on cosmic messengers, various forms of information that travel across space to reach us. The most important messenger is light itself, electromagnetic radiation spanning an enormous range of wavelengths. The light we see with our eyes represents only a tiny sliver of the electromagnetic spectrum. There are radio waves with wavelengths measured in meters or even kilometers. There are microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays with wavelengths smaller than atoms. Each wavelength range reveals different aspects of the cosmos. Radio waves show us cold gas clouds and the remnants of ancient supernovae. Infrared radiation penetrates dust clouds to reveal forming stars. Visible light shows us stars and galaxies as they appear directly. Ultraviolet light traces hot young stars. X-rays reveal extremely hot gas and active black holes. Gamma rays mark the most violent events in the universe, like exploding stars and colliding neutron stars. To study the universe properly, we need to observe across the entire electromagnetic spectrum. But Earth's atmosphere blocks most wavelengths. Only visible light and some radio waves make it through the atmosphere to ground level. This is why space telescopes are so valuable. By placing telescopes above the atmosphere, we can observe wavelengths that never reach the ground. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by providing crystal-clear views in visible and ultraviolet light without atmospheric distortion. The Spitzer Space Telescope observed in infrared. The Chandra X-ray Observatory studies the X-ray universe. The James Webb Space Telescope, launched in 2021, peers into the infrared to see the most distant and earliest galaxies, looking back to when the universe was only a few 100 million years old. Ground-based telescopes have also become incredibly sophisticated. Modern observatories use adaptive optics, systems that rapidly adjust mirror shapes to compensate for atmospheric turbulence, achieving image quality nearly as good as space telescopes. The largest ground-based telescopes now have mirrors 8 to 10 meters in diameter, able to gather enormous amounts of light from faint distant objects. But light isn't the only messenger from space. In recent years, we've opened entirely new windows on the universe. In 2015, the LIGO Observatory made the first direct detection of gravitational waves, ripples in space-time itself, created by colliding black holes. This wasn't electromagnetic radiation. It was the fabric of space, literally vibrating as gravitational waves from a cosmic cataclysm pass through Earth. Gravitational wave astronomy is still in its infancy, but it's already revealed black hole mergers and neutron-star collisions that would have been invisible to conventional telescopes. Future space-based gravitational wave detectors, like the planned LISA mission, will detect waves from supermassive black hole mergers across cosmic distances, providing yet another way to study the universe's structure and evolution. We also detect neutrinos, ghostly particles that barely interact with ordinary matter. Neutrinos are produced in nuclear reactions in the Sun, in supernova explosions, and in other high-energy cosmic events. Because they interact so weakly, they travel through space unimpeded, carrying information from the cores of stars and from the early universe that light cannot provide. Neutrino observatories, often built deep underground or under ice to shield them from other particles, detect these rare interactions. Cosmic rays, high-energy particles from space, provide another source of information. These particles, mostly protons and atomic nuclei, accelerated to tremendous energies, bombard Earth constantly. By studying their energies and trajectories, we learn about the most violent acceleration processes in the universe, from supernova shockwaves to active galactic nuclei. All these messengers, light across all wavelengths, gravitational waves, neutrinos and cosmic rays, carry information encoded in various ways. The wavelength of light tells us about energy and temperature. The redshift tells us about distance and cosmic expansion. The polarization tells us about magnetic fields. The spectrum tells us about chemical composition and physical conditions. Each piece of information is a clue that helps us reconstruct the cosmic story. But gathering the data is only the first step. We then have to interpret it, to figure out what it means. This is where theoretical physics becomes essential. We use mathematical models based on our understanding of fundamental physics to predict what we should observe under different conditions. We then compare these predictions to actual observations. When theory and observation agree, we gain confidence that we understand what's happening. When they disagree, we know something is wrong with either the observations or the theory, and we have to figure out which. This process of comparison between theory and observation has driven enormous progress in cosmology. Einstein's general relativity predicted that massive objects should bend light, that the universe should be either expanding or contracting, and that gravitational waves should exist. All these predictions have been confirmed by observation, giving us confidence that general relativity accurately describes gravity and space-time. Similarly, the Big Bang theory made specific predictions about the cosmic microwave background, about the ratio of hydrogen to helium in the universe, about the distribution of galaxies, and about how the universe should appear at different distances and times. All these predictions have been confirmed, establishing the Big Bang as our best understanding of cosmic history. But cosmology also has an important tool that other sciences sometimes lack, which is the ability to run computer simulations. We can't create a second universe to experiment on, but we can create virtual universes inside supercomputers. We start with initial conditions, matching what we observe in the early universe. Then we apply the laws of physics, letting gravity, expansion, and other forces evolve the simulation forward in time. These simulations are incredibly complex. A state-of-the-art cosmological simulation might track billions of particles representing dark matter, follow how gas heats and cools and forms stars, include feedback from supernovae and black holes, and evolve the universe forward through billions of years of cosmic time. The computations require some of the world's most powerful supercomputers running for weeks or months. When the simulations finish, we can compare the virtual universe they produce to the real universe we observe. Do the simulated galaxies look like real galaxies? Does the cosmic web structure match? Are the galaxy sizes and properties similar? When simulations successfully reproduce what we observe, it validates our understanding of the underlying physics. When they fail, it tells us something is missing from our models. The interplay between observation, theory, and simulation creates a powerful cycle of understanding. Observations provide the facts we need to explain. Theory provides the mathematical framework for explanation. Simulations test whether our theories really work when applied to complex systems. Each component checks and validates the others. But there's something important we need to acknowledge. Every measurement has uncertainty. Every observation has error bars. When we say the universe is 13.8 billion years old, that number has an uncertainty of about 20 million years. When we say omega equals 1, we mean it equals 1 within our measurement precision of about 0.5%. These uncertainties don't mean we don't know anything. They mean we know the range within which the true value must lie. Scientists are scrupulously honest about uncertainties. In fact, quantifying uncertainty is one of the hallmarks of good science. When you see scientific papers, they always include error bars on their measurements, confidence intervals on their conclusions, and discussions of systematic uncertainties that might affect the results. This rigorous treatment of uncertainty is what allows scientific knowledge to be reliable, even though individual measurements are imperfect. There's also the crucial process of independent confirmation. When one team makes an important discovery, other teams try to replicate it using different methods or different instruments. The discovery of cosmic acceleration, for instance, was made by two independent teams using different telescopes and different supernovae. The fact that both teams got the same answer dramatically increased confidence in the result. The cosmic microwave background has been measured by multiple satellites, COBE, WMAP and Planck, each more sensitive than the last. The consistent picture that emerged from these independent missions gives us confidence that we're really seeing the ancient light from the early universe and not some artifact of the instruments. Peer review is another critical component of how science works. Before a result is published in a scientific journal, it's reviewed by other experts in the field who check the methods, look for errors, and assess whether the conclusions are justified by the data. This process, while imperfect, catches many mistakes and ensures that published results meet community standards. There's also something beautiful about how different measurements of cosmic properties all fit together consistently. When we measure the age of the universe from the cosmic microwave background, from the expansion rate, and from the ages of the oldest stars, we get consistent answers. When we measure the composition of the universe from different methods, gravitational lensing, galaxy motions, supernova distances, they all point to the same proportions of ordinary matter, and dark energy. This consistency across independent measurements gives us confidence that we're understanding reality correctly. But we must remain humble about what we know. Large parts of our cosmological model remain mysterious. We don't know what dark matter is made of. We don't know what dark energy is, or why it has the value it does. We don't have a working theory of quantum gravity. We can't observe what happened in the first tiny fraction of a second after the Big Bang. We don't know whether the universe is truly infinite or just much larger than we can see. Science is not about achieving perfect certainty. It's about progressively reducing uncertainty, building models that work better and better at explaining observations, and being willing to change our minds when new evidence demands it. The history of cosmology shows this process at work. The steady-state model of an eternal, unchanging universe gave way to the Big Bang, when evidence of expansion and the cosmic microwave background became overwhelming. The accelerating universe overturned assumptions about cosmic deceleration when supernova observations demanded it. What we know about the universe's shape and structure rests on an extraordinary foundation of careful observation, mathematical theory, and computational simulation, all cross-checked through independent measurements and subjected to rigorous peer review. We know these things as well as we know anything in science, but we also know that future observations might surprise us. that deeper theories might reveal new layers of reality we haven't imagined, and that the cosmos will always retain some mystery, some aspects beyond our current ability to measure or comprehend. The methods of cosmology represent humanity at its best, using reason and observation to understand our place in the grand scheme of existence. The fact that these methods work, that they allow tiny creatures on a small planet to comprehend the shape and history of the entire universe, is perhaps as remarkable as any specific discovery we've made. It shows that the universe is fundamentally comprehensible, that nature operates according to principles that minds can grasp, and that human beings, for all our limitations, possess the intellectual tools to understand the cosmos that gave birth to us. Chapter 20. Challenges to the Standard Model. We've painted a picture of a universe that's remarkably well understood. Space is flat. The universe is expanding and accelerating. It's composed mostly of dark matter and dark energy, with ordinary matter making up only 5%. Cosmic structure grew from tiny quantum fluctuations in the early universe. Everything fits together in what cosmologists call the Standard Model of cosmology, also known as the Lambda CDM model. Lambda represents dark energy as a cosmological constant, and CDM stands for cold, dark matter. This model has been spectacularly successful. It explains countless observations across different wavelengths and distance scales. It makes predictions that have been confirmed again and again. By any reasonable standard, the Lambda CDM model ranks among the greatest achievements of human science. But we need to talk about its problems, its tensions, and the observations that don't quite fit as well as they should. Science progresses not by ignoring difficulties, but by confronting them honestly. Small discrepancies between theory and observation sometimes turn out to be measurement errors that disappear with better data. But sometimes they're the first hints of new physics, cracks in the current model that point toward deeper understanding. The history of science is full of examples where anomalies that seemed minor at first eventually overturned entire frameworks. One of the most significant current tensions involves the expansion rate of the universe, a quantity called the Hubble constant. This number tells you how fast the universe is expanding at the present cosmic time. It's measured in units of kilometers per second per megaparsec, which tells you how much faster two galaxies are receding from each other for every megaparsec of distance between them. Here's the problem. When you measure the Hubble constant using observations of the early universe, particularly the cosmic microwave background, you get one value. The most recent analysis from the Planck satellite gives about 67 kilometers per second per megaparsec. But when you measure it using observations of the late universe, particularly using supernovae and other distance indicators, you get a different value. Recent measurements using Cepheid variables and supernovae give about 73 kilometers per second per megaparsec. That might not sound like a big difference. It's less than 10%. But the measurements are precise enough that the difference is statistically significant. It's not just noise or measurement error. Multiple independent teams using different methods consistently find this tension. Either the early universe measurements are wrong, or the late universe measurements are wrong, or something about our understanding of how the universe evolved is incomplete. This discrepancy is called the Hubble tension, and it's been growing more severe as measurements improve rather than resolving. Scientists have checked and rechecked everything. They've looked for systematic errors in the measurements, problems with the distance indicators, issues with the cosmic microwave background analysis. The tension persists. What could explain it? One possibility is that our model of how the universe evolved from early to late times is missing something. Maybe dark energy isn't quite constant, but changes slightly over time. Maybe there's additional physics we haven't accounted for. Maybe the expansion rate actually varies in ways we don't expect. Any of these possibilities would require modifying the standard cosmological model in some way. Another possibility is that the measurements themselves have subtle problems we haven't identified. Distance measurements in astronomy are notoriously tricky because they rely on chains of reasoning. You calibrate one distance indicator using another, which was calibrated using another, creating a cosmic distance ladder. If any rung of that ladder is slightly off, it throws off all the subsequent measurements. Perhaps there's a systematic error somewhere in this ladder that hasn't been found yet. There's also something called the sigma-8 tension. This involves measurements of how clumpy the universe is, how much structure exists at different scales. Different methods of measuring the clumpiness give slightly different answers. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background don't quite agree on how much matter has clumped together over cosmic history. Again, the differences are not enormous, but they're statistically significant and persistent. This could indicate problems with measurements, or it could suggest that something about structure formation isn't captured correctly in the standard model. Maybe dark matter has properties we haven't accounted for. Maybe gravity behaves slightly differently on certain scales. Or maybe it's a statistical fluke that will disappear with more data. These tensions have led some scientists to propose alternatives to the standard cosmological model. One alternative idea is to modify the laws of gravity on large scales. A theory called MOND, which stands for Modified Newtonian Dynamics, suggests that gravity works differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. This could potentially explain galaxy rotation without dark matter. But MOND has significant problems. While it can explain some galaxy rotation curves without dark matter, it fails to explain gravitational lensing observations, the cosmic microwave background, and the large-scale structure of the universe. It also lacks a relativistic formulation that would be needed to make precise cosmological predictions. Most cosmologists view MOND as an interesting idea that ultimately doesn't work. Other scientists have proposed that maybe dark energy isn't a cosmological constant, but something more dynamic, a field that changes over time. These models, sometimes called quintessence, can be constructed to match current observations while making different predictions about the universe's far future. But they introduce additional complexity without yet providing clear predictions that distinguish them from the simpler cosmological constant. There are also attempts to modify general relativity itself on cosmic scales. These modified gravity theories try to explain cosmic acceleration without dark energy by changing how gravity behaves over enormous distances. Some of these theories make testable predictions, but so far none has proven clearly superior to general relativity with a cosmological constant. The scientific community remains cautious about abandoning the standard model based on these tensions. History teaches us to be skeptical of revolutionary claims. Extraordinary claims require extraordinary evidence. The lambda CDM model explains literally thousands of independent observations. Any alternative model needs to explain all of those observations at least as well, plus resolve the tensions, plus not contradict anything else we know. That's a very high bar. It's entirely possible that the current tensions will be resolved by better measurements rather than new physics. Uncertainties in distance measurements might be larger than currently estimated. Subtle, systematic errors might exist in how we extract information from the cosmic microwave background. Statistical fluctuations might make the clumpiness appear different than it really is on average. But it's also possible that we're seeing the first hints of physics beyond the standard model. Maybe there's an additional component to the universe we haven't discovered yet, sometimes speculatively called early dark energy. Maybe neutrinos have properties that affect cosmic evolution more than we thought. Maybe dark matter interacts with itself in ways we haven't considered. Any of these possibilities could affect cosmic expansion and structure formation in ways that might resolve the tensions. What makes this situation exciting rather than troubling is that we have the observational and theoretical tools to investigate. New telescopes are coming online that will measure cosmic expansion with unprecedented precision. The Vera Rubin Observatory will map the universe in exquisite detail. The Euclid space mission will measure the expansion history using multiple methods. The James Webb Space Telescope is seeing farther back in time than ever before, testing our models of early galaxy formation. These new observations will either resolve the tensions by finding the sources of error, or they'll make the tensions worse by confirming the discrepancies with better data. If the latter happens, that will be genuinely exciting, because it will mean we're on the verge of discovering new physics, new aspects of reality that the current model doesn't capture. The existence of tensions and anomalies doesn't mean we don't know anything. It means we don't know everything, which is completely different. The lambda CDM model is clearly capturing something real and important about the universe. Whether it's the complete story or just an approximation that works well in the regime we've tested is what current research is trying to determine. Science thrives on this kind of productive tension between what we're confident about and what remains uncertain. The standard model isn't dogma to be defended at all costs. It's a working hypothesis to be tested rigorously and modified or replaced if evidence demands it. The willingness to question even our most successful theories when observations suggest they might be incomplete is what allows science to progress. The challenges to the standard model remind us to maintain appropriate humility about our knowledge. We've learned an extraordinary amount about cosmic shape and structure, but mysteries remain. The universe might still have surprises in store, aspects of its nature that current observations only hint at. And that's exciting. The universe that taught us everything we know might soon teach us that there's more to learn. Depths to reality that our current framework doesn't quite capture. For scientists, there's no better prospect than the possibility of discovering something genuinely new. Chapter 21. The Future of Exploration. We've traced the history of how humans came to understand the universe's shape, from ancient Greek philosophers to modern satellite observations. We've explored the current state of knowledge, where space appears flat and the cosmos is dominated by mysterious dark matter and dark energy. But now I want to look forward. What comes next? What new tools and techniques will push our understanding even deeper? What questions might we answer in the coming decades that seem impossible to address today? The future of cosmology is incredibly bright. A new generation of telescopes and instruments is either being built or already beginning operations, each designed to probe aspects of the universe that previous generations of instruments couldn't access. These aren't just incremental improvements, they represent quantum leaps in our ability to observe the cosmos and test our theories. Let's start with ground-based telescopes. 3 enormous next-generation observatories are under construction or in planning stages. The extremely large telescope in Chile will have a main mirror 39 meters in diameter. The 30-meter telescope planned for Hawaii will have, as the name suggests, a 30-meter mirror. And the giant Magellan telescope, also in Chile, will combine 7 mirrors to create an effective diameter of 25 meters. To put these sizes in perspective, the largest current ground-based telescopes have mirrors about 10 meters across. These next-generation telescopes will have collecting areas more than 10 times larger, allowing them to gather far more light from faint, distant objects. With adaptive optic systems that can compensate for atmospheric turbulence, they'll achieve angular resolution comparable to space telescopes while having much larger collecting areas. What will these telescopes do? They'll see the very first galaxies forming in the early universe. They'll directly image exoplanets around nearby stars, studying their atmospheres to search for signs of life. They'll measure the properties of dark energy with unprecedented precision by observing thousands of distant supernovae and mapping the cosmic web in exquisite detail. They'll study the centers of galaxies where supermassive black holes lurk, watching matter swirl around event horizons and testing general relativity in extreme conditions. In space, the James Webb Space Telescope, launched in late 2021, is already transforming our view of the early universe. Its enormous mirror and infrared instruments can peer through cosmic dust and see light from galaxies that formed when the universe was only a few 100 million years old. Early results from Webb have already surprised scientists by showing that galaxies in the early universe were more massive and structured than theoretical models predicted. Webb will be joined by other space missions in the coming years. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky. It will map the distribution of dark matter using gravitational lensing, measure the expansion history of the universe using supernovae, and search for exoplanets through microlensing. The European Space Agency's Euclid mission, launched in 2023, is specifically designed to study dark energy and dark matter. It will create a three-dimensional map of over 1 billion galaxies across more than a third of the sky, measuring both their distances through redshift and their shapes to study gravitational lensing. This massive survey will trace the cosmic web's structure and measure how it evolved over 10 billion years of cosmic history. For studying the cosmic microwave background, several ground-based observatories are pushing to higher sensitivity and precision. The Simons Observatory in Chile and the CMB-S4 project, a network of telescopes at the South Pole and in Chile, aim to measure the polarization of the cosmic microwave background with exquisite precision. They're searching for a specific pattern called B-mode polarization that would be the smoking gun signature of gravitational waves from cosmic inflation. If these observatories detect primordial gravitational waves, it would be one of the most important discoveries in cosmology. It would confirm that inflation really happened and provide information about the energy scale and mechanism of inflation. It would be our first direct observational window into the physics of the very first moments after the Big Bang, when the universe was a tiny fraction of a second old and quantum gravity effects were important. Gravitational wave astronomy is also entering a golden age. The LIGO and Virgo detectors that made the first gravitational wave detections are being joined by additional detectors. Kagra in Japan is already operating. New detectors in India and Australia are planned. With more detectors spread around the globe, we'll be able to pinpoint the sources of gravitational waves more accurately and detect weaker signals. But the most transformative development in gravitational wave astronomy will be the launch of space-based detectors. The LISA mission, a collaboration between NASA and the European Space Agency planned for the mid-2030s, will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart. These spacecraft will use lasers to measure tiny changes in the distances between them caused by passing gravitational waves. LISA will detect gravitational waves at much lower frequencies than ground-based detectors can access. This means it will observe supermassive black hole mergers across the universe, the in-spiral of smaller objects into supermassive black holes, and potentially gravitational waves from phase transitions in the very early universe. These observations will test general relativity in regimes we've never probed before and provide completely new information about cosmic structure and evolution. Neutrino astronomy is also advancing. The IceCube Neutrino Observatory at the South Pole, which uses a cubic kilometre of Antarctic ice as a detector, has already detected high-energy neutrinos from distant cosmic sources. Upgrades to IceCube and new neutrino telescopes in the Mediterranean Sea and Lake Baikal in Russia will detect more neutrinos and trace them back to their sources with better precision. Neutrinos carry unique information because they're produced in environments that are opaque to light, like the cores of supernovae and the jets of active galactic nuclei. By combining neutrino observations with electromagnetic observations and gravitational wave detections, a new field called multi-messenger astronomy provides complementary views of the same cosmic events, revealing aspects that no single type of observation could uncover alone. The search for dark matter is intensifying. Deep underground laboratories around the world are running ever more sensitive experiments to detect dark matter particles interacting with ordinary matter. These experiments shield their detectors from cosmic rays and other backgrounds, waiting for the rare moment when a dark matter particle might scatter off an atomic nucleus. So far, direct detection experiments haven't found dark matter particles, but they've ruled out large regions of parameter space, narrowing down where dark matter might hide. Each generation of experiments is an order of magnitude more sensitive than the last. If dark matter consists of weakly interacting massive particles in the mass range these experiments probe, we might detect them in the next decade or two. There are also indirect searches for dark matter. If dark matter particles can annihilate each other, they should produce gamma rays, neutrinos, or other particles that we could detect. Satellites and ground-based telescopes are searching for excess emissions from regions where dark matter is concentrated, like the centers of galaxies or nearby dwarf galaxies. Hints of possible signals have been reported, but nothing conclusive yet. Particle accelerators continue to push the energy frontier. The Large Hadron Collider at CERN, which discovered the Higgs boson in 2012, continues to run at higher energies, searching for new particles and new physics. Future colliders, possibly 100 kilometers in circumference, are being discussed. These might produce dark matter particles or other exotic particles that would shed light on fundamental physics beyond the standard model of particle physics. Quantum technologies are also opening new possibilities. Quantum computers, if they can be scaled up, might allow us to simulate the universe at a level of detail impossible with classical computers. Quantum sensors might detect incredibly weak signals like ultralight dark matter or high-frequency gravitational waves. Quantum communication might enable new kinds of astronomical observations by linking widely separated telescopes with quantum entanglement. Artificial intelligence and machine learning are transforming how we analyze astronomical data. Modern surveys produce petabytes of data, far more than humans could examine manually. Machine learning algorithms can identify patterns, classify galaxies, detect anomalies, and extract information from complex datasets in ways that would have been impossible a generation ago. AI might even help us discover new physical laws or relationships hidden in the data. All these technical advances will address specific questions about the universe's shape and structure. We'll measure the Hubble constant more precisely using multiple independent methods, hopefully resolving the current tension. We'll determine the properties of dark energy, whether it's truly constant or evolving, and whether it's described by a cosmological constant or requires a more complex model. We'll map the distribution of dark matter with unprecedented detail, testing whether it behaves exactly as predicted by current models. We'll measure the curvature of space to even greater precision. Current observations suggest space is flat to within about 0.5%. Future observations might improve this to 0.1% or better. We'll search for any deviation from perfect flatness, any hint that omega isn't exactly 1, which would have profound implications for cosmic topology and the physics of inflation. We'll look for signatures of cosmic topology, patterns in the cosmic microwave background, or in the distribution of galaxies that would indicate space wraps around on itself. We'll search for evidence of bubble collisions from eternal inflation, circular patterns in the CMB that would show our universe once bumped into a neighboring bubble. We'll try to detect primordial gravitational waves that would confirm inflation and probe physics at energies approaching the Planck scale. We'll study the very first galaxies and stars, understanding how the universe transitioned from smooth plasma to the complex structure we see today. We'll trace the evolution of cosmic structure across billions of years, testing our models of how gravity amplified tiny initial fluctuations into galaxies and clusters. We'll observe black holes in unprecedented detail, testing whether their behavior matches general relativity's predictions or reveals deviations that point to new physics. And we'll keep searching for surprises, for observations that don't fit our models, for anomalies that hint at physics beyond what we currently understand. The history of science shows that some of the most important discoveries were unexpected, things that appeared in the data that no one had predicted or even imagined. The next few decades will be an extraordinary time for cosmology. We're not at the end of discovery. We're not running out of questions. If anything, we're entering a new golden age where our observational capabilities are expanding faster than ever before, where multiple approaches are converging on the deepest questions about cosmic structure, and where genuine surprises might be waiting just beyond the edge of current knowledge. For anyone fascinated by questions about the universe's shape, origin and fate, this is a thrilling time to be alive. We're living through the era when many of these ancient questions are finally being answered with precision and confidence, when observation and theory are combining to reveal the cosmos's deep structure. And we're also living through the era when new questions are emerging, mysteries that previous generations couldn't even formulate because they lacked the observational foundation. The future of cosmic exploration is not just about confirming what we think we know. It's about venturing into genuinely unknown territory, about probing aspects of reality that remain mysterious despite all our progress, and about being open to the possibility that the universe might be stranger, more subtle and more wonderful than even our most imaginative current theories suggest. Chapter 22. What if we're wrong? Before we wrap up our journey through cosmic geometry, I want to spend some time on an uncomfortable but essential question. What if we're wrong? What if some fundamental assumption underlying everything we've discussed turns out to be mistaken? What if future observations or theories overturn our current understanding just as dramatically as the Big Bang overturned the static universe, or as cosmic acceleration surprised astronomers in the late 1990s? This might seem like an odd question to ask after spending so much time explaining what we know. But considering the possibility of being wrong isn't a sign of weakness in science. It's a sign of strength. It's what distinguishes science from dogma. Science is a process of progressively refining our understanding, and that process requires acknowledging that even our best current theories are provisional, subject to revision if new evidence demands it. History provides sobering reminders of how confident scientists can be about frameworks that later prove incorrect or incomplete. In the 18th century, chemists were absolutely certain that combustion involved the release of a substance called phlogiston. They had elaborate theories about phlogiston flow and could explain many observations in terms of it. But phlogiston didn't exist. Combustion is actually about oxygen combining with other elements, and the phlogiston theory was entirely wrong, despite seeming to work for decades. In the 19th century, physicists were convinced that light waves travelled through a substance called the luminiferous ether that filled all of space. They developed detailed models of the ether's properties and designed ingenious experiments to measure Earth's motion through it. But the ether didn't exist. Light doesn't need a medium to propagate through. The ether theory was abandoned when special relativity provided a better framework. For thousands of years, the geocentric model, with Earth at the centre of the cosmos, seemed obviously correct. After all, we don't feel the Earth moving. The Sun appears to orbit around us. The stars seem fixed to a celestial sphere. It took overwhelming evidence from telescopes and the explanatory power of Newtonian mechanics to overturn this deeply intuitive but incorrect model. So, what assumptions in modern cosmology might future generations look back on as quaint or misguided? Let's consider some possibilities. One foundational assumption is the cosmological principle. The idea that on large enough scales the universe is homogeneous and isotropic, looking roughly the same everywhere and in all directions. This assumption is well supported by observations. The cosmic microwave background is remarkably uniform. The distribution of galaxies on the largest scales appears homogeneous. But what if we're being fooled by selection effects? We can only observe a finite region of the universe, a sphere whose radius is determined by how far light can travel in the time since the Big Bang. This observable universe might be homogeneous, while the larger universe beyond our horizon is wildly inhomogeneous, with vast regions of different density or even different physics. We'd have no way to know because we can't see beyond our cosmic horizon. In some eternal inflation scenarios, different regions of the larger universe could have radically different properties. Our observable universe might be an unusually uniform patch in a much more chaotic, larger reality. All our cosmological models assume the cosmological principle, but if it's only locally true in our patch rather than globally true everywhere, many of our conclusions about cosmic geometry might need revision. Another assumption is that we correctly understand the nature of dark matter and dark energy. We've inferred their existence from gravitational effects and from cosmic expansion. But what if we're misinterpreting these observations? What if there's no dark matter and gravity just works differently on large scales than general relativity predicts. What if there's no dark energy, and cosmic acceleration is actually telling us that the universe's expansion has been misunderstood in some fundamental way? Most cosmologists are confident that dark matter and dark energy are real because so many independent lines of evidence point to them. But history shows that when observations require invoking mysterious invisible substances to explain them, we should remain at least slightly skeptical. Phlogiston was invoked to explain combustion. The ether was invoked to explain light propagation. Both were eventually recognized as unnecessary once better theories emerged. Now, dark matter and dark energy are much better established than phlogiston or ether ever were. The evidence is far more diverse and compelling. But intellectual humility demands we acknowledge the possibility, however small, that some future theory might explain all the observations without requiring these mysterious components. There's also the possibility that we're misunderstanding the nature of time and cosmic history. The Big Bang model rests on running cosmic expansion backward to infer a hot, dense beginning about 13.8 billion years ago. But what if the expansion rate hasn't been constant in ways we don't understand? What if there are systematic errors in how we measure cosmic distances or ages? What if time itself behaves differently in the early universe than our theories assume? Some alternative cosmologies propose that the Big Bang wasn't the beginning, but rather a transition from a previous contracting phase. Others suggest that what we interpret as a beginning might be an artifact of how we're modelling time in quantum gravity. These alternative frameworks are speculative and face significant challenges, but they remind us that even the Big Bang, well established as it is, represents an inference from observations rather than something directly witnessed. We should also consider the possibility that we're living in a simulation. This isn't as crazy as it might sound. If it's possible to create realistic simulations of universes, and if technological civilizations eventually develop the capability to run such simulations, then there might be many more simulated universes than real ones. In that case, statistical reasoning suggests we're more likely to be in a simulation than in the base reality. If we are in a simulation, the universe's shape might be defined by the algorithms and computational substrate of whatever is running the simulation rather than by fundamental physics. The laws we observe might be emergent properties of code rather than bedrock reality. There might be no way to detect this from within the simulation, but it would mean our entire framework for understanding cosmic geometry is based on a mistaken premise about the nature of existence. This isn't a hypothesis most scientists take seriously for practical purposes because it's not testable and doesn't lead to different predictions. But it's worth considering as a reminder of how assumptions about the nature of reality underlie all our scientific reasoning. There's also the humbling possibility that our current observations are simply insufficient to constrain cosmic geometry definitively. We observe the universe from one location at one time. We see light that's had billions of years to travel to us, but that light can only tell us about conditions along the specific paths it travelled. Could there be large-scale structure or variations that our observations simply miss? Some cosmologists have worried about whether the part of the universe we can see is truly representative of the whole. What if we happen to live in an unusual region, a kind of cosmic bubble or void, and the properties we measure are not typical of the universe as a whole? Some observations, like apparent alignments in the cosmic microwave background that seem to break statistical isotropy, have fueled speculation that maybe our location isn't as random as we assume. Most attempts to explain observations through assuming we're in a special location run into problems with the Copernican principle, the idea that we shouldn't assume we're in a privileged position. But the Copernican principle is an assumption, not a proven fact. Future observations might conceivably reveal that we do occupy an unusual location, which would force major revisions to cosmological models that assume typicality. We should also acknowledge the limits of human cognition. Our brains evolved to understand medium-sized objects moving at moderate speeds in 3 spatial dimensions. We're trying to use these evolved cognitive tools to understand the geometry of the entire universe across scales from quantum foam to cosmic horizons. It's remarkable that we can do this at all, but there might be aspects of reality that our minds are fundamentally ill-equipped to grasp. The mathematics might be clear, the equations might make predictions, but our understanding, our intuitive grasp of what the math means, might be limited by cognitive constraints. We might be like the proverbial fish trying to understand water, so immersed in our assumptions about space and time that we can't imagine alternatives that might be closer to the truth. All that said, I want to emphasize that the possibility of being wrong doesn't mean we are wrong, or that we don't know anything. The evidence for cosmic expansion, the Big Bang, the cosmic microwave background, the large-scale structure of the universe, all of this is overwhelming and comes from multiple independent sources. The standard cosmological model is almost certainly capturing something real and important about the universe. But perfect certainty is neither possible nor necessary in science. What matters is that our models work, that they make accurate predictions, that they fit diverse observations, and that we remain open to revising them if evidence demands. The Lambda CDM model does all of this extraordinarily well. Whether it's the final word or an approximation that will eventually be superseded by something deeper is a question for future observations to decide. The willingness to consider that we might be wrong is actually what gives us confidence when we say we're right. It's because we've questioned our assumptions, tested our models rigorously, looked for alternative explanations, and found that the evidence consistently supports our conclusions, that those conclusions carry weight. Science earns its credibility not through claiming certainty, but through honest engagement with uncertainty and willingness to change course when necessary. The shape of the universe, as we currently understand it, flat spatial geometry in an expanding space-time, rests on an extraordinary foundation of evidence. Future observations will either strengthen this foundation or reveal cracks that point toward new physics. Either outcome represents progress. Either outcome brings us closer to understanding the nature of reality. And maintaining the humility to acknowledge we might be wrong is essential to ensuring we're asking the right questions and interpreting the answers honestly. Chapter 23. Philosophical Implications. We've spent most of our time exploring the scientific understanding of cosmic shape, examining observations, theories, and measurements. But now I want to step back and consider what it all means. The universe's shape and structure raise profound philosophical questions about existence, meaning, probability, and our place in the grand scheme of things. These questions don't have definitive answers the way scientific questions sometimes do, but they're worth contemplating because they touch on fundamental aspects of what it means to be human, to be conscious, to exist in this particular universe. Let's start with perhaps the most haunting question. Are we alone? This ancient question takes on new dimensions when we understand the universe's vastness. In an infinite flat universe, there would be infinitely many galaxies, infinitely many stars, infinitely many planets. The conditions that led to life on Earth, however improbable, would necessarily occur infinitely many times across infinite space. In fact, in an infinite universe, there wouldn't just be other planets with life. There would be planets exactly like Earth, with people exactly like you, living lives that are identical to yours in every detail. This sounds absurd, but it's a logical consequence of infinity combined with quantum mechanics. If there are infinite possible locations and quantum mechanics says every possible configuration has some non-zero probability of occurring, then every possible configuration will occur somewhere, infinitely many times. This means that somewhere in an infinite universe, there's another planet where someone exactly like you is reading these exact words at this exact moment. There's a planet where everything is identical to Earth, except that you made a different decision at some crucial point in your life. There are infinite variations on your existence, playing out across infinite space. The concept is called quantum immortality, or the infinite copies problem, and it raises deeply strange questions about identity and meaning. If there are infinite copies of you, what makes you special? What makes your specific experiences and choices matter when they're being duplicated infinitely many times elsewhere? Some philosophers find this deeply troubling, suggesting it undermines the significance of individual existence. Others argue it doesn't change anything practically, that your experience remains unique to you even if it's duplicated elsewhere, and that meaning comes from the internal experience rather than from being unique in an absolute sense. This connects to something called the measure problem in cosmology. If the universe is infinite, how do you calculate probabilities? Normally, probability is the number of outcomes you're interested in divided by the total number of possible outcomes. But if both numbers are infinite, the fraction is undefined. You can't do the division. Different ways of counting lead to different probability assignments, and we have no principled way to choose between them. This isn't just an abstract philosophical puzzle. It affects how we make predictions and test theories. If we can't calculate what we should expect to observe in an infinite universe, how do we test cosmological models? Some physicists think this problem is fatal to certain versions of eternal inflation and the multiverse. Others think we just need to find the right mathematical framework for handling infinities. The question of free will, also takes on interesting dimensions in light of cosmic geometry. If the universe has a block structure where all of space-time exists eternally, past, present and future equally real, does that mean the future is already determined? If your entire life exists as a four-dimensional structure in space-time, does that mean your choices are illusions, that everything was always going to happen exactly as it does? This is the ancient philosophical problem of determinism, but physics gives it new urgency. The laws of physics, as we understand them, are deterministic in the sense that given complete information about a system at one time, you can, in principle, calculate its state at any other time. Quantum mechanics introduces randomness, but it's randomness governed by probability rules, not human agency. Where in all this does free will fit, if it exists at all? Some philosophers argue that free will is compatible with determinism, that what matters is not whether your actions are predetermined by the laws of physics, but whether they flow from your own desires and reasoning. Others maintain that genuine free will requires the universe to be fundamentally open, with the future not fully determined by the past. The shape and structure of space-time don't resolve this debate, but they inform it, showing us what kind of universe we're having the debate within. The flatness of space also connects to deep questions about fine-tuning. Why is the universe's density so exquisitely balanced at the critical value? Why are the fundamental constants of nature adjusted to values that permit complex chemistry, stars and life? One possible answer is the anthropic principle, that we observe these values because we couldn't exist to observe different values. But is this a genuine explanation, or just a tautology? In a single universe, the fine-tuning seems to cry out for explanation. The odds of getting all these constants right by chance seem astronomically small. This has led some people to infer design, a cosmic creator who set the parameters to permit life. Others invoke the multiverse, arguing that if there are countless universes with different parameters, the existence of at least one with our values becomes unsurprising, and we necessarily find ourselves in that one. But the multiverse explanation raises its own philosophical problems. If we explain our universe's properties by appealing to unobservable other universes, have we left the realm of science for metaphysics? Is a theory that requires infinite unobservable entities to explain observed facts really more satisfying than accepting the observed facts as brute givens? Different philosophers and scientists land in different places on these questions. There's also the question of whether mathematics is discovered or invented. We've learned that the universe's shape can be described with exquisite precision using mathematical equations. General relativity uses the mathematics of differential geometry to describe curved spacetime. Quantum mechanics uses complex vector spaces and operators. The cosmic microwave backgrounds pattern can be analyzed using spherical harmonics and statistical correlation functions. Why does mathematics work so unreasonably well at describing nature? Is mathematics somehow built into the fabric of reality, existing independently of human minds, and we're discovering its structure? Or is mathematics a human invention, a language we've created, and it works well because we've deliberately designed it to describe patterns we observe. This question about the relationship between mathematics and physical reality has puzzled thinkers for millennia. Some physicists and philosophers go further, suggesting that reality is mathematics, that the physical universe is fundamentally a mathematical structure, and what we call matter and energy are just particular patterns within that structure. In this view, sometimes called mathematical Platonism or the mathematical universe hypothesis, asking why math describes the universe is like asking why words describe language. The universe doesn't just follow mathematical laws. It is mathematical in its essential nature. The vastness of space raises questions about cosmic loneliness and connection. We're separated from other galaxies by distances light takes millions or billions of years to cross. We'll never visit those distant realms. Any civilizations that might exist in other galaxies are forever beyond our reach due to the expansion of space. Does this cosmic isolation make existence more meaningful or less? Does it matter that we're connected to the rest of the universe only through ancient light that's been traveling for eons? Some find existential comfort in the universe's vastness, feeling that being part of something so grand gives perspective on daily concerns and connects us to something larger than ourselves. Others find it terrifying or depressing, emphasizing how small and insignificant we are against the cosmic backdrop, how brief our existence is compared to cosmic timescales. But there's another perspective. We're not separate from the cosmos. We're made of atoms forged in ancient stars. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created in stellar furnaces and scattered through space by supernova explosions. You're literally made of stardust, assembled by billions of years of cosmic evolution. Far from being separate from the universe, you're one way the universe has organized itself to become conscious of its own existence. This leads to perhaps the deepest philosophical question the universe's shape and history raise. Why does the universe exist at all? Why is there something rather than nothing? Understanding that space is flat, or that the universe began 13.8 billion years ago, doesn't answer this question. Even a complete theory of physics that explained every observation would still face the question, but why these laws and not others, or why any laws at all? Some philosophers argue this question is unanswerable in principle, that any proposed answer just pushes the mystery back one level. If you say the universe exists because of some prior cause, you then have to explain why that cause exists. If you say the universe is self-caused or necessarily existing, you still haven't explained why necessary existence is possible or how something can cause itself. The question might be one that exceeds human cognitive capacity to answer. Others suggest the question might dissolve under careful analysis, that it rests on assumptions about causation or existence that don't apply at the most fundamental level. Maybe asking why the universe exists is like asking what's north of the North Pole, a question that seems meaningful but actually isn't, because it violates the structure of the system it's asking about. The universe's shape, age, and structure don't provide ultimate answers to these philosophical questions. but they provide the context in which we ask them. They inform our understanding of what kind of reality we inhabit. They show us whether the cosmos is eternal or temporal, infinite or finite, structured or chaotic, designed or natural. And knowing these things, even if they don't resolve all philosophical questions, gives us a foundation for thinking about meaning, purpose, consciousness and existence with greater clarity and depth. Philosophy without science risks becoming untethered from reality, spinning elaborate theories about a universe that doesn't actually exist. Science without philosophy risks losing sight of why the questions matter, reducing wonder to data points. Together, science and philosophy, observation and reflection, measurement and meaning, give us the fullest possible picture of the universe and our place within it. Chapter 24, The Timeline of Cosmic Understanding. It's worth stepping back and appreciating the remarkable journey humanity has taken to reach our current understanding of cosmic shape. This hasn't been a smooth progression of steady advancement. It's been a story of brilliant insights and stubborn misconceptions, of revolutionary breakthroughs and decades of patient observation, of lone geniuses and collaborative teams, of ideas rejected and later vindicated, of confident theories overturned by unexpected discoveries. For most of human history, cosmic questions were answered through mythology and theology rather than observation and reason. Different cultures told different creation stories, imagined different cosmic structures, assigned different meanings to celestial phenomena. These stories served important cultural functions, connecting communities to the heavens and providing frameworks for understanding existence. But they weren't science in the modern sense because they didn't systematically test their claims against observation. The ancient Greeks, particularly starting around 2,500 years ago, pioneered a new approach. Thinkers like Thales, Anaximander, Pythagoras and Aristotle began asking questions about cosmic structure and attempting to answer them through logic and observation, rather than appealing to divine revelation. They established that the Earth is spherical, that celestial motions follow patterns, and that mathematical reasoning could illuminate natural phenomena. This was revolutionary, even though many of their specific conclusions were wrong. For nearly 2,000 years, the Ptolemaic geocentric model dominated Western thinking about cosmic structure. Earth sat immobile at the center. The sun, moon, planets and stars all orbited around us on complex systems of circles and epicycles. This model worked reasonably well for predicting planetary positions, and it aligned with both common-sense observation and religious teachings about humanity's central importance. It took extraordinary evidence and theoretical insight to overturn such a well-established framework. The Copernican revolution, beginning in 1543, displaced Earth from the cosmic center. Galileo's telescopic observations, starting in 1609, provided visual evidence supporting Copernicus. Kepler's laws of planetary motion, published between 1609 and 1619, showed that planets follow elliptical orbits according to precise mathematical relationships. Newton's Principia in 1687 explained these motions through universal gravitation and laws of motion. By 1700, educated Europeans understood that Earth orbits the Sun, that gravity governs celestial mechanics, and that the same physical laws apply in the heavens as on Earth. But cosmic structure beyond the solar system remained mysterious. Were the stars fixed to a celestial sphere, or did they exist at different distances? Was the Milky Way the entire universe, or were there other island universes beyond it? How large was the cosmos, and how old? These questions wouldn't be answered for another 2 centuries. The 19th century brought spectroscopy, the ability to analyze light from distant objects and determine what they're made of and how they're moving. This revealed that stars are made of the same chemical elements found on Earth. It showed that some nebulae are gas clouds, while others might be more distant. It allowed measurement of stellar velocities through the Doppler shift. Photography allowed long exposure images, capturing faint objects invisible to the eye. Together, these tools transformed astronomy from recording positions and brightnesses to investigating physical properties and distances. The early 20th century brought 2 revolutionary developments. Einstein's general relativity, published in 1915, revealed that gravity is curvature of space-time, and that the universe itself has a geometry determined by its matter and energy content. And Hubble's observations in the 1920s proved that spiral nebulae are distant galaxies and that the universe is expanding. These discoveries overturned the static eternal cosmos that everyone had assumed and revealed a universe with a history, a beginning, and a dynamic character. The mid-20th century saw the development of the Big Bang theory, the realization that cosmic expansion implies a hot, dense origin. Gamow, Alpha, and Herman predicted the cosmic microwave background in the 1940s. Its accidental discovery by Penzias and Wilson in 1964 provided definitive confirmation that the Big Bang really happened. Suddenly, cosmology was an observational science with precise predictions that could be tested against measurements. The late 20th century brought increasingly sophisticated observations across the electromagnetic spectrum. Satellite missions like COBE measured the cosmic microwave background from space. Surveys mapped the 3-dimensional distribution of galaxies, revealing the cosmic web. Observations of distant supernovae revealed cosmic acceleration in the late 1990s, completely unexpected and pointing to dark energy dominating the universe. The 21st century has seen cosmology become a precision science. The WMAP and Planck satellites measured cosmic microwave background properties to percent-level precision. Large surveys have catalogued hundreds of millions of galaxies. Gravitational wave detectors opened entirely new windows on the universe. Computer simulations have become sophisticated enough to model cosmic evolution in remarkable detail. We now know the universe's age to better than 1% precision, its composition to a few percent, and its geometry to better than 0.5%. Each step in this journey built on previous work, while sometimes overturning previous conclusions. The cumulative nature of scientific knowledge means that even when paradigms shift, much of the previous understanding remains valid in its domain of applicability. Newtonian mechanics wasn't wrong. It was incomplete, a limiting case of Einstein's relativity that works perfectly well at low speeds and weak gravity. Similarly, our current understanding will likely prove incomplete in ways we haven't yet discovered, but it will remain valid in the regime we've tested. The timeline of cosmic understanding also shows the importance of technological innovation. Every major advance in observational cosmology has come from new instruments opening new windows on the universe. Galileo's telescope, spectroscopy, photography, radio astronomy, space-based observatories, gravitational wave detectors, each expanded what we could observe, and therefore what we could know. Future understanding will similarly depend on future instruments pushing into currently inaccessible regimes. It's also worth noting how international and collaborative modern cosmology has become. While ancient and medieval astronomy was often isolated in particular cultures, modern cosmology involves scientists from every continent working together, sharing data, building on each other's work. The cosmic microwave background satellites have been international collaborations. The gravitational wave detectors involve hundreds of institutions. Major surveys combine data from observatories worldwide. This collaborative character ensures that results are robust and that diverse perspectives contribute to progress. The journey from ancient stargazers wondering about the heavens to modern cosmologists measuring the universe's shape to sub-percent precision is one of humanity's great intellectual achievements. It shows what becomes possible when careful observation, mathematical reasoning, and willingness to revise beliefs in light of evidence are sustained over generations. Each generation has stood on the shoulders of those before, seeing a bit further, understanding a bit more deeply. And we're not at the end of this journey. We're in the middle of it. The questions our ancestors asked, what is the shape of the cosmos? How did it begin? Where is it going? Are questions we've made extraordinary progress on but haven't fully answered. Future generations will look back on our current understanding as we look back on Ptolemy or Newton, respecting the achievements while recognizing the incompleteness. The timeline of cosmic understanding extends from the distant past into the indefinite future, and we're privileged to be alive during a particularly rich chapter. Chapter 25. Personal perspectives from scientists. Behind all the equations and observations, behind the telescopes and satellites and simulations are human beings. Scientists who've devoted their lives to understanding cosmic structure. People who spend nights at remote mountaintop observatories, who analyze data for years seeking subtle patterns, who develop theories attempting to make sense of observations, who experience the joy of discovery and the frustration of unsolved problems. I want to share some of their perspectives on what it's like to study the universe's shape and what motivates this work. Vera Rubin, who discovered the first compelling evidence for dark matter, once described the experience of looking through a telescope at distant galaxies as almost spiritual. Here were vast collections of hundreds of billions of stars, so far away that their light had travelled for millions of years to reach her eyes. And she could measure how they moved, probe their structure, learn their properties. She spoke of feeling deeply connected to the cosmos through this work, of experiencing awe every time she observed. The dark matter discovery that made her famous came from patient observation, measuring galaxy after galaxy, noticing a pattern that contradicted expectations. Rubin also faced significant barriers as a woman in astronomy during the mid-20th century. She was discouraged from pursuing science, denied access to certain observatories, had her work dismissed or attributed to male colleagues. Her persistence despite these obstacles and her eventual recognition show both how much progress has been made in making science more inclusive and how much talent was historically wasted by artificial barriers. Her perspective reminds us that understanding cosmic shape is a human endeavor subject to human limitations and biases. Saul Perlmutter, who led one of the teams that discovered cosmic acceleration, described the moment when they realized what their supernova observations meant as terrifying and exhilarating simultaneously. They'd been confident they knew what they'd find, that expansion was slowing down. The data saying otherwise seemed impossible. They spent months checking everything, convinced they must have made an error. The possibility that the universe's most basic behavior was opposite to expectations was so radical that accepting it required overcoming deep-seated assumptions. But Perlmutter also emphasized the importance of following the evidence wherever it leads, even when it leads somewhere unexpected and uncomfortable. Science isn't about confirming what you already believe. It's about discovering what's true, even when it contradicts your preconceptions. The discovery of dark energy represents science working exactly as it should. Observations forcing revision of theories even when the new picture seems strange. Jocelyn Bell Burnell, who as a graduate student discovered pulsars, rapidly rotating neutron stars, provides perspective on how discovery actually happens. It's not usually a sudden flash of insight. It's careful attention to detail, noticing something unusual in data, following up systematically, and having the courage to report anomalies even when they might seem like instrumental artifacts. Her discovery came from noticing a bit of scruff on paper charts recording radio signals, investigating what caused it, and realizing it was a real signal from an astronomical source with properties unlike anything known. Bell Burnell's story also illustrates how recognition in science isn't always fair. Her advisor won the Nobel Prize for the discovery of pulsars, but she wasn't included despite having done the observational work and been first to recognize the signal's significance. She's been gracious about this, but it reminds us that the scientific enterprise, while striving for objectivity in evaluating evidence, remains subject to human biases in assigning credit and recognition. Many cosmologists speak about the privilege of working on fundamental questions. These aren't questions with immediate practical applications. Understanding whether space is flat or curved doesn't cure diseases or build better technology, at least not directly. Yet these questions touch on the deepest aspects of existence, on where we came from and where we're going, on the structure of reality itself. There's something profoundly meaningful about contributing to humanity's understanding of cosmic nature, even in small ways. There's also satisfaction in collaboration, in being part of an international community working together on shared problems. Modern cosmology requires large teams. No individual builds a satellite or analyzes petabytes of data alone. Scientists speak of the excitement when multiple groups independently confirm a result, when different approaches converge on the same answer. The collaborative nature of the enterprise provides checks against errors and biases while creating a sense of shared purpose. Scientists also talk about dealing with uncertainty and ambiguity. Research doesn't always lead to clear answers. Data can be noisy or contradictory, interpretations can be debatable. Most scientific careers involve far more false starts and dead ends than breakthroughs. Learning to persist despite setbacks, to maintain enthusiasm despite frustration, to find meaning in incremental progress rather than requiring dramatic discoveries, these are essential aspects of the scientific life. Many scientists describe being inspired by mentors, teachers who sparked their interest in cosmology or who guided them through challenging problems. The transmission of knowledge and passion from one generation to the next is crucial to scientific progress. Every senior scientist was once a student, inspired by someone who came before. And every student today might become the scientist who makes the next major discovery. This generational continuity creates a living link stretching back to ancient observers of the heavens. There's also the challenge and importance of communicating science to the public. The universe's shape matters not just to specialists, but to everyone. These discoveries belong to all humanity, and making them accessible to non-scientists is both a responsibility and an opportunity. Scientists who excel at communication speak of the joy in seeing someone's eyes light up with understanding, in knowing you've shared wonder and knowledge that might change how someone sees their place in the cosmos. Some scientists reflect on how studying the universe changes their personal perspective. When you spend your career thinking about cosmic scales, about billions of years and billions of galaxies, it affects how you view everyday concerns. Some find it provides valuable perspective, making personal problems seem smaller against the cosmic backdrop. Others worry about disconnection, about difficulty relating to people whose concerns are more immediate and terrestrial. Most find a balance, appreciating both cosmic grandeur and human-scale meaning. There's also intellectual humility that comes from recognizing how much remains unknown. Even scientists at the forefront of cosmology, people who know more than almost anyone about cosmic structure, will freely acknowledge the vast territories of ignorance, the questions we can't yet answer, the mysteries that remain despite all progress. This humility isn't weakness. It's honesty about the limits of current knowledge and openness to future discoveries that might surprise us. Scientists working on cosmic shape also reflect on the remarkable fact that we can do this work at all, that humans, with our finite brains and limited senses, can comprehend the structure of the entire universe. Our eyes can only see a narrow range of wavelengths. Our lifespans are infinitesimal compared to cosmic timescales. We're confined to one tiny planet. Yet, through instruments that extend our senses, mathematics that extends our reasoning, and collaboration that extends our individual capabilities, we've managed to measure cosmic geometry and trace cosmic history. This is perhaps as remarkable as any specific discovery. These personal perspectives remind us that science is ultimately a human endeavor. The universe's shape is described in equations and measured with instruments, but it's understood by people with hopes and fears, frustrations and joys, who make mistakes and have insights, who collaborate and compete, who are inspired and discouraged. The scientific understanding we've achieved represents countless hours of human effort, creativity, and dedication by people who found meaning and purpose in trying to comprehend the cosmos that gave birth to us. Chapter 26. Visualizing the invisible. One of the great challenges in cosmology is that most of what we're trying to understand is invisible in multiple senses. We can't see dark matter directly. We can't see dark energy at all. We can't see the curvature of space with our eyes. We can't directly perceive four-dimensional space-time or visualize higher dimensions. Yet we need to think about these things, communicate them, develop intuitions about them. How do we visualize what we cannot see? Scientists and science communicators use analogies, models, and representations to make the invisible comprehensible. The trampoline analogy for curved space-time is a perfect example. By imagining a massive object creating a dip in a stretched fabric, we can develop intuition for how mass curves space-time and how that curvature affects motion. The analogy isn't perfect. Real space-time is three-dimensional space plus time, not a two-dimensional surface. And the curvature isn't into a higher dimension we can see from outside. But despite these limitations, the trampoline analogy provides a mental handle on an otherwise abstract concept. The balloon analogy for cosmic expansion is another standard tool. Imagine galaxies as dots on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot, even though none of the dots is moving across the balloon's surface. This captures something essential about cosmic expansion, that it's not galaxies moving through space, but space itself growing. Again, the analogy has limitations. Real space is three-dimensional, not a two-dimensional surface. And there's no center to the expansion, no inside or outside to the balloon. But the analogy provides a starting point for understanding. Computer visualizations have become increasingly sophisticated and important. Modern simulations can track the evolution of billions of particles representing dark matter and gas, following their gravitational interactions over cosmic time. The output can be rendered as videos flying through virtual universes, showing how cosmic structure grows from subtle initial fluctuations into the cosmic web we observe. These visualizations let us see processes that take place over billions of years and across billions of light years, making the invisible visible in a different sense. Data visualization is also crucial for understanding observational cosmology. The cosmic microwave background is often displayed as a colorful oval showing temperature variations across the sky. Red regions are slightly hotter, blue regions slightly cooler. The variations are actually tiny, but by greatly exaggerating the color scale, we can see patterns that would otherwise be imperceptible. These images have become iconic, representing humanity's view of the infant universe. Galaxy surveys produce three-dimensional maps showing millions of galaxies scattered through space. These maps reveal the cosmic web, filaments and voids in the distribution of matter. By rotating and zooming through these maps, we can explore cosmic structure in ways that tables of numbers wouldn't permit. The visualizations transform abstract data into spatial representations our visual systems can process intuitively. But visualizations can also mislead if we're not careful. Every representation makes choices about what to show and how to show it. Color scales can exaggerate or minimize differences. Three-dimensional structures projected onto two-dimensional screens lose information. Analogies capture some aspects of truth while missing others. We have to maintain critical awareness that the map is not the territory, that visualizations are tools for understanding rather than direct windows onto reality. This is particularly important when trying to visualize higher dimensions or exotic topologies. A 3 torus, a flat space that wraps around in all 3 directions, cannot be directly visualized because it requires 4 dimensions to embed without distortion. We can create projections or use mathematical descriptions, but we can't see it the way we see a coffee mug. Does this mean we don't understand it? Not necessarily. Mathematical understanding can sometimes exceed visual intuition. We can work with equations describing higher dimensional spaces even if we can't picture them. Scientists themselves often work primarily with mathematics rather than visual intuition. The equations of general relativity don't have simple pictures associated with them. They're tensorial expressions relating geometric quantities in ways that can't be easily drawn. Yet physicists develop deep understanding by working with these equations, seeing patterns and relationships that might not be visually representable. Mathematics becomes its own form of visualization, revealing structure through symbols and relationships rather than images. There's an interesting tension between the mathematical and visual approaches to understanding. Some physicists are highly visual thinkers who need pictures and analogies to make sense of concepts. Others are more algebraic, comfortable working with equations without necessarily visualizing what they represent. Both approaches have strengths. Visual thinking can provide intuitive understanding and suggest new connections. Mathematical thinking can be more precise and can handle complexity that visual thinking cannot. The best understanding often combines both approaches. When communicating with the public, visual representations become even more important because most people aren't familiar with the mathematical formalism. Science communicators work hard to find analogies and images that convey essential ideas without oversimplifying to the point of distortion. It's a challenging balance. Make the analogy too simple, and it misleads. Make it too complex or qualified, and you lose your audience. Documentary filmmakers and visualization artists have developed remarkable techniques for depicting cosmological concepts. Animation can show processes unfolding over time. Camera movements can take viewers on journeys through space. Metaphorical imagery can represent abstract concepts. The combination of narration, music and visuals can create emotional engagement with intellectual content. These productions serve vital roles in sharing cosmic understanding beyond academic communities. Museums and planetariums provide opportunities for interactive visualization. You can explore simulated universes, zoom from human scales to cosmic scales, see how observations connect to theoretical predictions. These hands-on experiences make abstract concepts more concrete and memorable. Studies show that people retain information better when they interact with it rather than passively receiving it. Virtual reality and augmented reality technologies offer new possibilities for cosmic visualization. Imagine putting on a headset and finding yourself floating in a simulated universe, able to fly through the cosmic web, travel back in time to the Big Bang, or zoom down to quantum scales. These technologies could provide unprecedented intuitive understanding of cosmic structure by letting people explore it experientially rather than just hearing or reading about it. But we should also acknowledge the limitations and biases in all our visualizations. We see the universe through human eyes evolved to detect a narrow range of electromagnetic radiation. We process information through brains optimized for medium-sized objects and moderate speeds. Our cultural backgrounds affect how we interpret images and metaphors. What seems like a clear representation to someone from one culture might be confusing to someone from another. Color choices in visualizations, for instance, aren't neutral. We tend to associate red with heat and blue with cold, but this is culturally contingent. The decision to represent dark matter as blue wisps or purple clouds is arbitrary, chosen for aesthetic or practical reasons rather than because dark matter actually looks that way. We can't see dark matter at all. The visualization is entirely constructed. Despite these limitations and caveats, visualization remains an essential tool for understanding and communicating cosmic structure. The invisible becomes thinkable through careful use of analogy, representation, and imagination. We'll never see the curvature of space-time or the shape of the universe with our eyes. But through creative visualization and mathematical description, we can understand them with our minds. And that understanding, however it's achieved, represents a triumph of human imagination and intellect over the limitations of our senses. Chapter 27. The Answer and What It Means. We've traveled together through ancient philosophy, revolutionary physics, stunning observations, and deep mysteries. We've explored how scientists measure cosmic geometry, what dark matter and dark energy are, how the universe began, and how it might end. Now it's time to return to our original question and provide the clearest answer current science can give. What is the shape of the universe? Based on all available evidence, particularly from the cosmic microwave background, the distribution of galaxies, and the expansion history measured through supernovae, the universe is flat. Space at the largest scales obeys Euclidean geometry. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. The ratio of a circle's circumference to its diameter is exactly pi. All the geometric relationships you learned in school apply to the cosmos itself. More precisely, the curvature parameter omega appears to be equal to 1 to within about 0.5% uncertainty. When we add up all the matter and energy in the universe, ordinary matter at 5%, dark matter at 27%, and dark energy at 68%. The total density is almost exactly the critical density that corresponds to flat geometry. This remarkable fact that the universe is balanced so precisely between positive and negative curvature provides strong support for cosmic inflation, which predicts exactly this outcome. What does flatness mean for the universe's extent? A flat universe could be infinite, extending forever in all directions with no boundary or edge. If this is the case, there are infinitely many galaxies out there beyond what we can see, infinitely many stars, infinitely many planets. Everything that can exist does exist, infinitely many times across infinite space. Alternatively, a flat universe could have exotic topology that makes it finite despite being locally flat. Space might wrap around on itself in ways we haven't detected. The universe might be vast, but not infinite. Current observations only constrain topology on scales up to about the size of the observable universe. If space wraps on larger scales, we wouldn't be able to detect it with current instruments. The observable universe, the region we can possibly see, is about 93 billion light-years in diameter. This is larger than you might expect, given that the universe is only 13.8 billion years old, because space has been expanding while light travels. Objects whose light has been travelling for 13.8 billion years are now much farther away than they were when they emitted that light. But the total universe is likely much larger than the observable universe, possibly infinitely larger. We are limited in what we can see by the finite speed of light and the finite age of the universe. Beyond our cosmic horizon are regions we cannot observe and never will be able to observe, even in principle. If the universe is infinite, then the observable universe represents an infinitesimal fraction of the whole. The universe is also expanding, and that expansion is accelerating. Every galaxy beyond our local group is moving away from us, and distant galaxies are receding faster than nearby ones. This expansion is driven by dark energy, which appears to be a property of space itself. As the universe expands, more dark energy comes into existence because more space is created, maintaining constant density and driving ever faster expansion. What does this mean for the universe's future? Based on current understanding, cosmic expansion will continue forever, getting faster with time. In the extremely distant future, hundreds of billions of years from now, galaxies beyond our local group will recede beyond our cosmic horizon. Observers at that time will see a universe that appears almost empty, containing only their local cluster because everything else has been carried away by expansion. Stars will eventually burn out as they exhaust their nuclear fuel. New star formation will cease when available gas is consumed. Galaxies will evaporate as stellar encounters eject stars into intergalactic space. Black holes will form from stellar remnants and will themselves eventually evaporate through Hawking radiation. After an almost inconceivably long time, perhaps 10 to the power of 100 years, the universe will approach heat death, a cold, dark, nearly empty state of maximum entropy where nothing interesting can happen anymore. But this fate is based on assuming dark energy remains constant. If dark energy strengthens over time, expansion could accelerate so dramatically that it eventually tears apart galaxies, solar systems, planets, molecules, and even atoms in a big rip. If dark energy weakens or becomes negative, expansion could slow, stop, and reverse, leading to a big crunch. These scenarios are considered less likely than continued accelerating expansion, but we can't completely rule them out. The flatness of space means the universe is geometrically infinite, or very large if finite. The expansion and acceleration mean it will exist and evolve for extremely long times into the future. The dark matter and dark energy that dominate the universe's composition remain mysterious in their fundamental nature, reminding us that much remains to be discovered. What does all this mean for us, for humanity, for life in the universe? In one sense, it emphasizes how tiny and brief we are against the cosmic backdrop. Our entire species has existed for only a few 100,000 years, on a planet 4.5 billion years old, in a universe 13.8 billion years old. We occupy one planet, orbiting one star in one galaxy, among hundreds of billions. We're not at any special location. We're not made of special matter. We're temporary patterns of ordinary atoms that will disperse back into the cosmos when we die. But there's another perspective. We're part of the universe that has become conscious of itself. We're matter and energy organized in such a way that we can contemplate the cosmos that created us. The atoms in your body were forged in stellar furnaces, scattered through space by supernova explosions, gravitationally assembled into a planet, organized through billions of years of evolution into structures complex enough to think and wonder and understand. You're literally made of stardust, assembled by the universe to know itself. The fact that we can understand cosmic geometry, that tiny creatures on a small planet can measure the shape of space itself, is perhaps as remarkable as any property the universe possesses. The cosmos is comprehensible. Reality operates according to principles that minds can grasp. This connection between mind and cosmos, between inner mental experience and outer physical structure, is one of the deepest mysteries and most profound wonders of existence. Understanding the universe's shape doesn't provide direct practical benefits in the way medical research or technological development does. But it enriches human culture and expands the scope of human knowledge and wonder. It answers questions that people have been asking for thousands of years. It connects us across generations and cultures through shared curiosity about our cosmic home. And it reminds us that reality is vastly larger and stranger than everyday experience suggests. The universe is flat, or very nearly so. It's expanding and accelerating. It's ancient but not eternal, having begun 13.8 billion years ago in the Big Bang. It's composed mostly of mysterious dark matter and dark energy. It's possibly infinite in extent, and it's filled with structure on every scale, from quantum foam to cosmic web, all following comprehensible physical laws. This is the answer to our question based on current evidence. It's an answer that previous generations couldn't have given, and future generations might refine or revise. But it's the best answer humanity currently possesses, hard-won through centuries of observation, reasoning, and discovery. Why this matters to you. We've covered enormous ground in this exploration of cosmic shape, from ancient philosophy through modern observations to future prospects and philosophical implications. But before we conclude, I want to bring everything back down to human scale and address directly why any of this should matter to you personally. Why should you care about the shape of the universe? The most direct answer is that understanding the cosmos helps you understand your place in it. You're not separate from the universe. You're part of it. Every atom in your body was created in the Big Bang or forged in stars. The oxygen you're breathing right now was produced billions of years ago through nuclear fusion in a star that later exploded, scattering its contents into space. That oxygen was incorporated into the gas cloud that collapsed to form our solar system, eventually becoming part of Earth's atmosphere and then part of you. The same fundamental particles and forces that shape galaxies also shape your body. The same quantum mechanics that governed the early universe also governs the chemistry of your cells. The same gravity that curves space-time on cosmic scales also keeps you on Earth's surface. Understanding the universe at large scales provides context for understanding yourself at small scales. You're not an isolated entity. You're an integrated part of the cosmic whole. Understanding cosmic scale also provides valuable perspective on daily life. The problems that occupy your attention, your worries and stresses and concerns can feel overwhelming. But against the backdrop of cosmic history, of billions of galaxies and billions of years, many personal problems shrink in perceived importance. This isn't to say your problems don't matter. They matter to you, and that's what counts. But cosmic perspective can sometimes help you distinguish between what's truly important and what's merely urgent or anxiety-provoking. Some people find existential comfort in cosmic understanding. Knowing you're part of something so vast and ancient can make individual existence feel more meaningful rather than less. You're not just living your life in isolation. You're participating in the universe's ongoing evolution, in the process by which matter becomes conscious and comprehends its own nature. That's a profound form of participation, of connection to something larger than yourself. The research that led to understanding cosmic shape has also produced practical benefits, though that wasn't its primary purpose. Satellites measuring the cosmic microwave background required developing incredibly sensitive detectors that found applications in medical imaging. The mathematical techniques used to analyze galaxy distributions inform data analysis methods across many fields. The GPS navigation system in your phone requires accounting for general relativity, for the fact that time passes differently at different heights in Earth's gravitational field. Understanding space-time curvature has direct practical applications. More broadly, the pursuit of fundamental knowledge for its own sake, without immediate practical application, represents one of humanity's noblest endeavors. Not everything has to have practical utility to be worthwhile. Beauty, art, music, poetry, philosophy, none of these are practically necessary for survival. But they're essential for human flourishing, for a life that's truly meaningful rather than merely functional. Understanding cosmic structure belongs in this category. It enriches human existence whether or not it helps anyone build better technology. Science education and scientific literacy matter for functioning in modern society. We face collective challenges, climate change, pandemics, resource management, that require scientific understanding to address effectively. Citizens who understand how science works, how evidence is evaluated, how theories are tested and revised, are better equipped to make informed decisions about policies affecting society. Cosmology, while removed from most practical concerns, provides an excellent case study in how science works at its best, how observation and theory combine to produce reliable knowledge about aspects of reality we can't directly experience. The knowledge we have about cosmic shape was built by previous generations and passed down to us. It's a gift from the past, from people who spent their lives pursuing understanding they knew they might not live to see fully developed. We have a responsibility to receive this knowledge gratefully, to preserve and extend it, and to pass it on to future generations in improved form. Caring about cosmic structure is a way of honoring those who came before and caring for those who come after. There's also something inspiring about the fact that humans can do this, that we aren't limited to understanding only our immediate environment, but can comprehend the structure of reality itself across all scales. We're creatures who evolved to hunt and gather on African savannas, yet we've developed tools and concepts that let us peer into the first moments after creation and measure space's geometry. This demonstrates the power of human reason, cooperation, and curiosity. It shows what becomes possible when we work together across generations toward shared understanding. For young people especially, learning about cosmic structure can open career possibilities and inspire educational paths. The scientists discovering exoplanets, measuring gravitational waves, analyzing cosmic microwave background data, they were all once students, learning about the universe and feeling that spark of wonder and curiosity. Maybe you're that student. Maybe reading or watching this will plant a seed that grows into a scientific career. Even if not, exposure to these ideas enriches education and expands horizons. Understanding the universe also influences how different cultures and societies see themselves and their place in existence. When humans believed Earth was the center of the universe, that cosmic belief shaped philosophy, religion, art, and social structures. The Copernican revolution, displacing Earth from cosmic centrality, had reverberations far beyond astronomy. It affected how we understood humanity's importance and relationship to the divine. Our current understanding that we inhabit one planet among countless others in a vast, possibly infinite universe, similarly shapes modern thought and culture. There's also the sheer wonder and beauty of what we've learned. The fact that space is curved by matter and energy. The fact that the universe began in unimaginable heat and density and evolved over billions of years into the complex structured cosmos we observe. The fact that we can see light that's been traveling for over 13 billion years, carrying information from when the universe was a fraction of its current age. The fact that most of the universe is invisible, composed of dark matter and dark energy we don't yet understand. These aren't dry facts. They're astonishing insights into reality's nature. Finally, caring about cosmic shape connects you to a human conversation that extends across millennia. Ancient philosophers wondered about the heavens. Medieval scholars contemplated the celestial spheres. Renaissance astronomers revolutionized cosmic understanding. Modern cosmologists measure space's geometry. And future generations will carry this conversation forward, answering questions we haven't even formulated yet. When you engage with these ideas, when you wonder about cosmic structure, you join this conversation. You become part of humanity's ongoing dialogue with the universe. So why does the universe's shape matter to you? Because you're made of universe. Because cosmic perspective enriches understanding of your place in existence. Because the knowledge is beautiful and inspiring. Because it represents human achievement and potential. Because it connects you across time and culture. Because understanding the largest scales illuminates the smallest scales. Because you're part of the cosmos contemplating itself. You don't need to become a cosmologist. You don't need to master the mathematics. Simply knowing that space is flat, that the universe is expanding, that we can measure these things and understand them, that enriches your relationship with reality. It makes the night sky more meaningful. It makes existence more profound. It connects you to something vastly larger than everyday concerns, while also revealing that you're intimately connected to that vastness. The universe's shape is your shape too, because you're not separate from the cosmos. Understanding it is a way of understanding yourself. We began this journey with a simple question. What is the shape of the universe? We've traveled through ancient civilizations, revolutionary physics, stunning discoveries, persistent mysteries, and profound implications. Now, as we conclude, let's reflect on where we've been and what we've learned. The universe is flat. This simple statement represents the culmination of thousands of years of human inquiry, from Greek philosophers reasoning about Earth's shape to satellite observations mapping ancient light across the cosmos. Flat means that space on the largest scales follows Euclidean geometry, that parallel lines stay parallel, that the fundamental rules of distance and angle that seem intuitive to us actually apply to the universe as a whole. This flatness emerged from conditions in the very early universe, probably during a period of cosmic inflation when space expanded faster than light in the first tiny fraction of a second after the Big Bang. That rapid expansion smoothed out any initial curvature, leaving space geometrically flat, or so close to flat that we can't measure any deviation. The universe is also expanding, and that expansion is accelerating. Galaxies are rushing away from each other as space itself grows. Dark energy, a mysterious component that makes up 68% of everything that exists, drives this acceleration. The universe will expand forever, becoming ever colder, ever emptier, approaching but never quite reaching a state of absolute zero temperature and maximum entropy. Most of what exists is invisible to us. Dark matter, 5 times more abundant than ordinary matter, provides the gravitational scaffolding on which galaxies and cosmic structure formed. Dark energy, even more abundant, pushes space apart and determines cosmic destiny. Together, these invisible components constitute 95% of the universe. Everything we can see directly, all the stars and galaxies and gas, represents only 5% of the whole. The universe had a beginning. Time and space came into existence about 13.8 billion years ago in the Big Bang. Before that moment, there was no before in any conventional sense. The cosmos has a history, an evolution from simple initial conditions to complex structures. Tiny quantum fluctuations in the early universe grew over billions of years into galaxies, stars, planets, and eventually life and consciousness. We know these things through remarkable observations across all wavelengths of light, through gravitational waves, through neutrinos, through careful analysis of ancient light that's been traveling across the cosmos for over 13 billion years. We know them through mathematics that describes how space and time curve under the influence of matter and energy. We know them through computer simulations that reproduce the universe's structure by applying physical laws to initial conditions. But we also know how much we don't know. We don't know what dark matter is made of. We don't know what dark energy fundamentally is, or why it has the value it does. We don't know whether the universe is infinite or just very large. We don't know whether other universes exist beyond our cosmic horizon. We don't have a working theory of quantum gravity that can describe the very first instant of the Big Bang. We don't know whether space is truly continuous or granular at the smallest scales. These gaps in understanding aren't failures. They're opportunities. They're the questions that will drive research for decades to come. They're the mysteries that will inspire future generations of scientists. The universe that revealed so much might still have profound surprises in store. What makes this story so remarkable is that we can tell it at all. Humans, tiny creatures on a small planet, have managed to measure the geometry of space itself. We've traced cosmic history from the first fraction of a second after creation to the present day. We've determined that we live in a flat, possibly infinite universe dominated by mysterious dark components. This represents an extraordinary achievement of human curiosity, creativity, and cooperation. Every culture throughout history has told stories about cosmic origins and structure. But our story is special because it's not just made up. It's not myth or speculation. It's based on observations that anyone can in principle verify, on mathematics that anyone can learn, on logic that anyone can follow. The universe's shape, as we understand it, represents knowledge in the deepest sense, beliefs that are justified by evidence and reasoning. This knowledge belongs to everyone. It was built by people from every continent and culture. It's shared freely across borders and generations. When children anywhere in the world learn that the universe is expanding, that space is curved by matter, that we can see light from when the cosmos was young, they're receiving a gift from all the scientists and thinkers who came before. and they might contribute their own insights, extending understanding for those who come after. The journey from wondering about the stars to measuring cosmic geometry represents one of humanity's greatest achievements. It shows what becomes possible when we combine careful observation with mathematical reasoning, when we build on previous work, when we remain open to revising beliefs in light of evidence, when we work together toward shared understanding. But this journey isn't over. It will never be over. There will always be deeper questions, subtler mysteries, aspects of reality that exceed our current comprehension. The universe is vast beyond imagination and subtle beyond easy understanding. We've learned extraordinary amounts, but we've also discovered how much remains to learn. Every answer raises new questions. Why is the universe flat? What is dark energy? Are there other universes? What happened at the very instant of the Big Bang? Can we detect primordial gravitational waves? Does space have exotic topology? What's the ultimate fate of everything? These questions will occupy scientists for generations, and their answers will likely surprise us just as past answers surprised previous generations. For now, we know the shape of the universe. We know it's flat or very nearly so. We know it's expanding and accelerating. We know it's ancient but finite in age. We know it's possibly infinite in extent. And we know we're part of it, made from its matter, governed by its laws, participating in its evolution. This is the answer we've been seeking. Space is flat. The universe is vast and dynamic and filled with mystery, and somehow, improbably, beautifully, this cosmos has organized itself in such a way that part of it, the part that is you, can contemplate the whole. You're the universe examining itself, matter becoming conscious of its own existence and structure. That might be the most remarkable shape of all. Not the geometry of space, profound as that is, but the shape of consciousness, the fact that the cosmos curves back on itself in a loop of self-awareness. You're that loop. You're where the universe becomes able to ask, what is my shape? And then, through science and reason and observation, discovers the answer. Keep looking up. Keep wondering. Keep asking questions. The universe that taught us everything we know still has secrets to share. And you're part of the ongoing story of cosmic understanding, a story that stretches from the ancient past into the unlimited future, a story that reveals we're all children of the stars, living in a universe more beautiful and strange than our ancestors ever imagined. The shape of the universe is flat space in expanding time. But the shape of your relationship with that universe, the contours of wonder and understanding and connection you feel, that shape is uniquely yours. Treasure it, share it, pass it on. Because understanding where we are and how we got here and where we're going, that's part of what makes us human. That's part of what makes existence meaningful. That's the gift the universe has given us, and the gift we can give back by continuing the search for truth about cosmic nature. The universe is flat, but the journey to understand it has been anything but simple, and the journey continues.